Morning, everyone.
Good morning.
Good morning.
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 Good morning. Good morning, Mr. Meglinski. You are chairing this session, right?
Yes, correct. Yes.
Yeah. Okay. My name is Buettner. I am the first speaker in the session.
Yeah. Very nice to meet you.
Okay. Hello. Good morning.
Yeah, and I think it's a time to start the session. So, and as the first speaker is already presented here, so I'm very pleased to say that he's given us a talk, and I think I'm sure actually this cheering with you, I believe, right?
Yes.
So is it okay? So if I'll start the session to chair and you continue?
One moment, I have one announcement. Good morning, everybody. Thus, we have some changes in our program because we have skipped one presentation by Professor Wang 2 days ago. And today, after presentation of Professor Masayada, will be the presentation of Professor Wang. And thus, we have a short break between two parts of the conference. Okay, thank you. Good luck.
Okay, thank you. Okay, please start.
I can start?
Yes.
Okay, thank you. Okay, good morning, everybody. I will share the screen. Okay, just a few moments. Okay. Okay, you should be able to see the screen and the pointer, okay? And you hear me?
Yep.
Okay, thank you very much. Then I will start. Good morning to the Ukraine and good morning, everybody, to the session. My name is Buettner. I am with the chair of Measurement and Sensor System Techniques from the Technical University of Dresden in Germany, and I'm happy to present this talk. It's called Closed Loop and Neural Network Aberration Correction Schemes for Correlation-based Laser Velocimetry. And it's about technical aspects of measurements from microfluidics. So microfluidics is more challenging and more exciting than most of you would expect, I think. And so this is what I'm going to talk about today. This is some example from microfluidics about active flows. It's this is a photocatalytic microswimmer where you have a photochemical reaction which is driving a flow. And so you can use of it for active microswimmers to transport drugs or delivery. And so you need an active motion of the microswimmer, and this is gained by the photocatalytic reaction. And you can see that there is some kind of quadrupole-like flow to the swimmer, which can drive micromotor. What is challenging for measurement? You can see the flow around is very complex, and it's three-dimensional in 3 dimensions, and it affects all 3 measurement velocity components, and we get very steep velocity gradients. This means the velocity is changing from 0 to a maximum value over a distance of a few micrometers. And these are challenging for measurement techniques. I'm going to talk about some even more challenging aspects, which are open interfaces in the vicinity of droplets. For example, you have gas bubbles, which play a role in transforming to renewable energies in terms of hydrogen generation. And on the other hand, you have levitated droplets. You have water droplets, for example, in fuel cells. So if you have fuel cells, then you have a chemical reaction from hydrogen and oxygen to water, and it is usually water vapor, which is carried out very easily, but sometimes under unfavorable conditions, you can have the case that you have formation of water droplets in the fuel cell, which block the microfluidic channels, of course, and then the efficiency will go down. And this effect is not completely understood so far. So there's an interaction of the airflow of the hydrogen and oxygen flow over the bubbles and with the bubble itself and the transport of the bubble. So if you increase the pressure, the bubble will be moved away, but this only appears under certain circumstances. And this is not yet clear when the droplets will start to move. So there are a lot of open questions between the interaction of the bubble and the grazing airflow. So for example, what is the flow within the bubbles and the droplets, and what is the connection of the inside flow in the droplet with the outside flow, with the outside airflow? What about stability of the droplets, and what about separation of the droplets and starting of the migration? So for all this, you can model this, but numerical simulation is quite difficult because you have a free open interface, which is hard to model in all terms, and the complex flow in the inside. So this is not entirely possible because of limited computational power, and this is why you have to make assumptions, and this can be checked by experiments only. And this is why I'm going to talk about measurement today. The problem is when you want to measure through the open interface, you have light refraction, and light refraction causes a lot of trouble for optic measurements, which you can see here. For example, you have deflection of the beam. So the deflection, the beam is not going in the original direction. On the other hand, you have some kind of lens effect, which increases the divergence of the beam. And all these things together affect the imaging of the flow. So the imaging works if you add some particles into the flow, and you image them and record them with a camera and evaluate the movement of the particle. Then you can see in a perfect case without optical distortions, you have very perfect scatterers in the flow, which you can very nicely see. And this sort of thing, you can make a good of measurement. But then if you have optical distortions, the particles appear blurred. And this, of course, which I will show you in the following, leads to increased measurement errors. Furthermore, we have complex 3D, 3C flow structures, like I've shown you. And we have, for example, an opaque substrate. So you cannot, this is, for example, the gas diffusion layer of the fuel cell, so that you cannot easily measure from below. There's only the chance to measure from the top through the fluctuating interface. And to make it even more challenging, you can see that the distortion, the optical aberration, is not constant, but it varies with time. So it's a time varying problem because of the grazing airflow. And you can see this in this video with increasing grazing flow, this bubble starts to shake more and more and more. Okay, this was my motivation, and this is the outline of my coming talk. I will shortly introduce correlation-based flow velocimetry. I will expand this to 3D measurements with point spread function engineering. This is the main part, the first main part of my talk, a closed loop aberration correction scheme with adaptive optics. I will present the Ferrando guide star, and the second part will be an actor-less neural network aberration correction scheme, which needs no actor but uses instead a neural network. Okay, so let's start. So what is imaging or correlation-based velocimetry? It's simply technique where you seed the flow to be investigated with particles, and you shine on light, which is expanded to a light sheet. So it's a very thin light sheet, so you can measure in one plane of it, and in this plane you observe the particles and you correlate the particles from two recordings, which I can show you more closely here. So the underlying image processing is just a cross-correlation function. You record two images, one at a time t and the one after a certain time interval delta t. In this time, the particles have moved a little bit, and you can evaluate the moving by or the displacement by applying the cross-correlation function between the two images. In fact, you didn't apply the function to the whole image, but you make some interrogation areas inside the flow, so that each interrogation area gives one vector arrow in the flow velocity field. And if you do it for all this, then you have the whole two-component vector field inside the plane. Okay, this works pretty well. This is a commercialized technique, but it cannot be so simply applied in microfluidics because the flow is highly three-dimensional, and we need some more to get the third component. This is okay, where we get into the open question of measurement techniques, how to gain the depth information, how to gain 3D measurements, how to affect optical distortions, the measurement results, and how can we correct for these dynamic distortions. And so the first thing we apply is a point spread function engineering. It is the case that you use, for example, a spatial light modulator where you display some kind of helical phase mask. It's a special helical phase mask which breaks the symmetry of the point spread function. You have no longer an angular symmetry in such a way that one scattering source is imaged to two objects on the camera. And this has a certain orientation angle psi, and you can evaluate the orientation angle, which is correlated to the depth. So that if you scan through the depth, you can see that this point spread function is virtually rotating, and by evaluating the angle, you can determine the depth. So this is the full 3D, 3C measurement. And this is an example of an airflow, which is taken through an opaque substrate. You have a resting water droplet on the substrate. You have a grazing airflow over it. The airflow induces a flow pattern inside the droplet, and we measured this flow pattern in a three-dimensional manner, and we can see that we have a complex two vortex structure. And yeah, we were first obviously to resolve this structure by a measurement, and we could see some interesting effect because the two vortices, the vortex pair, is tilted by an angle of plus minus 30 degrees. So this was an interesting observation. Another thing was, if you usually have a grazing airflow, you would assume that the airflow in the water droplet goes in the same direction with the grazing airflow. This is true, but only for very low velocities. If you increase the velocity more and more, then something interesting happens. There is a flow reversal, and the flow in the water droplet goes in the opposite direction than the airflow. And this is so some kind of totally counterintuitive, but it's an interesting effect to observe. Okay, so this obviously works, 3D particle localization and tracking. Okay, now we come to the optical distortions in the measurement. We can see here the original image of the particles carried in the flow. They look very perfect, or like point scatterers without distortion. And this is the correlation function where we can see in the middle a very sharp peak, which is the correlation peak, and which is used to evaluate the velocity. And this is very small and tiny, and it's located at the right position at the center. So we can measure a very good flow velocity profile. This is some kind of homogeneous flow just for testing the principle. So this works very fine. But if we now put some optical distortions in the beam path, for example, this is Zernike coma, and this is some other interposition of Zernike polynomials, then we can see that this affects not only the particles but also the correlation functions. We can see that the correlation peak gets broader. That means that we can not localize it as good as before, and that there's a shift from the away from the center, which means that we have a systematic deviation. And this is we can find themselves in the flow profile. So the flow profile looks completely different to that what we get in the undistorted case. We have a apparently higher velocity, which in fact is not there, but it seems to be higher, and also the fluctuation is higher. So if you consider this is our case without distortion, and this is our case with optical distortion inserted, then we can see that that the mean velocity is increased by almost 40%, and also the fluctuating velocity is increased. So the mean velocity as well as the fluctuating velocity are measured with a system with a significant measurement error. So we get statistic and systematic measurement errors by the optical distortions. Okay, this will affect also the double helix point spread function. Here we have simulated different optical distortions for the depth measurement, and we can see if we add astigmatism on the face mask or we add coma on the face mask, then we have a deviation from the angle, for example. This is the amplitude of the Zernike polynomial, and this is the angle. So that means usually you would expect a constant line, but we don't get this. We get also a dependency of the Zernike polynomial amplitude. That means that we get measurement deviation. In this case, the angle is affected, and we get a measurement error for the measurement, for the depth measurement. For coma, it's a little bit different. Then we get displacement in the X and Y direction. And so if we summarize this, so for an arbitrary distortion, we get measurement errors in X, Y, and Z position. So all components are affected. So there are some basic correction schemes from flow measurement. For example, you could use the background pattern, but this obviously cannot apply in the small scale gas diffusion layer of a microcell. Or you can use ray tracing, which is just simply too long to process this. Or you can use a hardware solution where you make refractive index matching. And refractive index matching is a well-known technique, but you cannot apply it, for example, for droplets, because the fluid itself is liquid and you need another liquid to match this. So these approaches work very well, but not for the case of the droplet. And they work mainly for static distortions, but not for dynamic distortions. Okay. So this is what I'm going to talk about today. We get inspired from astronomy. This is a more or less now established technique in astronomy. From earthbound telescopes, you can introduce adaptive optics scheme. This means you can introduce deformable mirrors, which compensate the fluctuation of the Earth's atmosphere. And so this application is quite similar, but there are some difficulties. But you can also see that here it's time-depending aberration, and it can be corrected. For example, the observatory in the Mauna Kea on Hawaii was one of the first telescopes with implemented adaptive optics, and you can see that it works pretty well. So without correction, you see only blurred images, and with adaptive optics correction, you see. But you can gain a much higher contrast, you improve spatial resolution, you improve the contrast, you improve brightness. So this is obviously a very promising technique. And the question is, can we apply this to droplets as well? We can see here a laser and a light modulator, which I'm going to talk about next, a wavefront sensor, and the control hardware and software. And so this is obviously a closed loop correction scheme. If you have a pre-distorted wavefront here, then it gets compensated or distorted by the water interface. Then we have a corrected wavefront in the water, and we can measure without distortion. So this is the basic principle. The question is, can we apply this in flow measurement? So we applied some deformable membrane mirror, which is from iPower company, which has 69 elements. And this is pretty fast, a 1.2 kilohertz bandwidth. So this is a promising component to apply. In this picture, you can see different Zernicke polynomials applied, quadrupole, tetrafoil, aberrations, astigmatism, and so on. And you can see the optical distortion in the image. For measuring the wavefront, you can use a Hartmann-Check wavefront sensor, which is also a common technique in astronomy. You use the displacement, you get the displacement tensor. From this, you can calculate step by step the distortion of the wavefront. This means the deviation of the wavefront from the default value. And if you like, you can decompose this into Zernicke polynomials, and you get a spectrum. So this is an example spectrum which we recorded from a droplet, and you can see that we get very high frequencies of several 10, or later we'll show several hundred hertz of the droplet. Okay, what you else need is a very good hardware platform. This we developed by ourselves, because this is some kind of special. You have very strong constraints in terms of latency and in terms of control rate, and we have made a decision towards an FPSoC, which is a field programmable system on chip, which is a combination of a CPU and a field programmable gate array. So you get the best of both worlds, from very fast computational power, but also from high level programming and software programming way. And so we achieve with this a 3.6 kilohertz control rate. And here we can see example measurement. This is an example flow seeded with particles. And we put some lens in it, and we move the lens up and down and as an optical distortions. You can see if the control loop is switched off, so there's no control, then the particles are blurred. So if you turn on the adaptive optics correction, then we can see that the particles remain sharp all the time when we move the lens, because it's actively controlled by the hardware. Just what you see, that the field of view is changing because of the magnification factor, but the particles itself, they remain sharp. So this works obviously. Okay, one further challenge is to measure through a single optical access only. If you have this case of a fuel cell, then we see here the gas diffusion layer, which is some kind of a porous layer. It's optically opaque, so you cannot measure through it. And then we need obviously a technique where we can measure only from one side. So we have to illuminate and detect from the same side, because we cannot simply measure, and that's why we need the adaptive optics correction, and how we can achieve this. And there we used some kind of new guide star concept, which we call the Fresnel reflex, or the Fresnel guide star. And here we simply make use of the Fresnel reflection of the water interface. So we have a refractive index jump from air to water, and you can get a small reflection of 2% of this. And this is obviously very low, but it's enough to make it use for measurement. The thing is, due to the locally varying profile, you get a locally varying distortion. And this is that if you measure the surface function of the water droplet, then we have all information about the optical distortion. So it should be fine to measure the reflex, and we get all information about the distortion, and we can conclude from the reflected beam to the transmitted beam. So we can estimate with an observer how the transmitted beam will behave in the water. And this is our concept. We use green laser, for example, to illuminate the droplet. we can measure the Fresnel reflex, which is directly reflects. It's the same wavelength, but with the same beam, we illuminate the particles inside the droplet. They shine light and they are fluorescent, so they change the wavelength, and we can use here some fluorescence filter or dichroic mirror to separate the elastically scattered light from the Fresnel reflex from the inelastically scattered fluorescent light. And we can use this to give it on the camera and to give it on the wavefront sensor, so we can measure the surface function and the flow inside independently. And this is the concept of the Fresnel guide star, so it's kind of wavelength multiplexing scheme. So this is how we realize this. This is a droplet on the surface, on the interface. This is the grazing airflow. This is microscope objective, and this is the PTV or PRV measurement technique. And this will go over an own path, which goes which includes the adaptive optic image correction. We use the deformable membrane mirror, the FPGA system, the wavefront sensor. So this is a closed loop correction. And this will correct the green beam, and at the same time, the red beam, the particle image is corrected, and we can measure it with the camera. Okay, so how good does it work? We have a problem to characterize this, because the flow, we do not know the flow, and we do not know our measurement system, and so we make some kind of characterization experiment. We use the micro channel with a laminar flow, and we know this is a very good parabolic profile with this. So this is a test case, and we put the optical distortions on the top of the micro channel. So this will cause optical distortion, and this will cause the flow. And so we have a decoupled flow. We know the flow, and we want to measure how good this works. And this is what we can see here. You can see here the particles. Obviously, these are the the double images of the particles. So every double point stands for one particle, and you can see that they have a certain or well-defined orientation angle in this case. This one has in this case, and this in this case, angle. So this appear to, obviously, they will come from different depths inside the droplet. Okay, and then I will start the video, and then we will see some flickering on the particles, which is the effect of the distortion. I hope you can see it, because you can see this is a very fast flickering. The droplet is fluctuating very fast. You can see the flickering, and if you switch on the optical image correction, then you can see that this flickering is obviously reduced in a very good way. So this obviously works good, but we need some quantitative measurement, and this we can see here. So if we apply no droplet, then we can measure the parabola in a very good way. It's very precise, 1 to 3% measurement error, static droplet. And now we have the fluctuating droplet on it. So we blow airflow on the droplet and it starts to shake. But we don't use the optical image correction, and we can see that there's a strong measurement error from this. We get a deformation of the profile, and we can see that the scattering, the variance is dramatically increased. And if we now turn on the correction, then we can see we can decrease this fluctuation quite good. And it works not perfectly to the undistorted case, but it's obviously a good gain in compared to the correction compared to the case where we do not apply a correction. So this works obviously. And then we can look, for example, at a measurement budget. This is a static case. We get a measurement from the PTV. This is the fluctuating part of the velocity, the variance. And we can see that we have from our just PTV camera measurement uncertainty of 1.8%. The turbulence from the flow itself is 0, because this flow is laminar. And we get a case from the dynamic aberration, which here goes up to almost 6%, but this is reduced drastically to 2 or 4, 3%. So this works off, obviously. So this is the part of the measurement uncertainty budget, which is reduced by the adaptive optics image correction. And see, here we can see the temporal spectrum. It extends to, this is decomposed into different Zernike polynomials. It goes over several hundred hertz. And yeah, so this is obviously a very fast process. I will come to this later. And so these are some results we achieved. For example, you can see here the gas diffusion layer. You can see the droplet. This was applied to a grazing airflow, and the particle starts to shake. And the question is, how can we measure the movement of the particle itself? And we have a look at the first vibrational eigenmode in the flow. And so if we do not, so this is the spectrum of the velocity of the droplet, and we can see the spectrum of the velocity, and we can see a clear peak. This peak is allocated to the first vibrational eigenmode, and we can see a clear difference between the adaptive optics and the non-adaptive optics case. This means without adaptive optics, this is the blue curve, the amplitude would be significantly underestimated, and this is correct. What we correct very, what the adaptive optics can correct very good. So we can see a significantly increase if we apply the adaptive optics, and so we can correct this underestimation and to get the true value in the flow. And we can also make this in a temporal resolved manner. So this is a phase and time resolved manner. If the particle is moving periodically, we can make a phase resolved measurement, and we can see how the velocity is distributed over the droplet independence of the phase, and we can see that this is from the amplitude underestimated, distributed over the whole droplet. Okay, so the result is that we can make spatially, temporally, and phase resolved flow measurements inside the tiny droplet with adaptive optics correction. Okay, so I will come to the second part of my talk. This works very well, but some components are crucial, which is the adaptive optical element. So there's a big choice available: deformable membrane mirror, liquid crystal on silicon. This means that we have piezoelectrostatic, electromagnetic actuators, chip and tilt tunable lenses, or liquid crystal on silicon. They all have some advantages, some disadvantages, some pros and cons, and in terms of amplitude and so on, but they all have their own limitations. And so the question is, what is the optimal adaptive optical element? And this is not so easy to say, because each spatial light modulator is limited by the temporal bandwidth, it is limited by the spatial frequency, that means the element count, and is limited by the amplitude range which it can display. And to make it a good aberration correction, you need to be good in all of these three regimes, and if you're not good, then obviously it will not work. So in particular, from the water surface, this is very challenging because we have a high temporal bandwidth, we have a high spatial frequency, and we need a high amplitude range, and this is difficult to fulfill from all available modulators. And so the question is, can we get rid of the modulator and make an alternative scheme? And the question is, yes, if we apply machine learning approaches. This is our multiple input unit, which was our idea. So we don't use adaptive elements anymore. We just use the distorted particle image. And now we want to use the Hartmann check sensor, which was very successful in measuring the surface function. And the idea was to give the surface sensor data, the wavefront sensor data, additionally into the neural network. So this is a multiple input unit. This means that we have two inputs, the distorted particle image and the wavefront sensor data, which we can measure. And as a result, we can get the uncorrected, the corrected particle image, the undistorted, the corrected particle image. So this is the idea. Or the basic idea is that without the wavefront sensor data, the correction will be very challenging because you don't have, you have many degrees of freedom, and we can have increased constraints if we apply the wavefront sensor data additionally. And this will get an unique, an unambiguous correction to the undistorted particles. Okay, so how does it work? Or how did we do this? This is a setup for training. We measured the surface function of the data, of the surface, with a laser. With the same laser in transmission, we measured the surface function, and later we displayed the distorted surface function on the deformable mirror, and the surface was let at rest. So we have the distorted particles which go to the Hartmann-Shack wavefront sensor and to the distorted camera input here. And at the same time, we have the undistorted particle image as the ground truth. So these three data are fed into the neural network like this for training. So we have the undistorted particles, we have the distorted particle image, and we have at the same time the allocated spot displacement tensor of the Hartmann-Shack sensor. And these are fed into the network for training. Okay, so once it is trained, we can use it for corrections. We feed the distorted images and the actual or the current spot displacement tensors into the network, and we get out the corrected particle image. And this is only then, if you want to apply this, this is for only the case for correction. This means we illuminate the flow with a laser. We record the surface function, the green curve, with a Hartmann-Shack wavefront sensor, and we record the particle image with a PIV camera. And so this is how it, these are the results, the particle images. These are the distorted, undistorted case, this is the distorted case, and this is the corrected case. And so if we subtract them, we can see a big difference for the distorted case. And for the undistorted case, the difference is minimized, which means that we can very closely receive the undistorted images as before. And yeah, we have some numbers here. So the peak signal to noise ratio is significantly increased if we apply this correction. And also the structural similarity index is increased if we apply the correction scheme. So obviously it works, and there is an improvement for the measurement. And this is also the result for the surface waves. For the flow measurement, this is some kind of nozzle flow going from the right to the left. This is the undistorted case without surface waves, our reference. So if we apply surface waves, then we get the distortion as we expect. And if we now correct it with a neural network scheme, then we get the same, almost the same case in the undistorted case. So obviously this works very well, and you can see this in the cross section as well. This is the velocity. In the distorted case, it goes down. There is this very significant systematic error, and this error is reduced and goes back to the undistorted case. Okay, so obviously this works, and I want to summarize my talk. Okay, so optical distortions obviously affect correlation-based velocimetry very drastically. We get measurement errors, systematic and statistic. We can apply some point spread function engineering technique to measure the depth of the particles and to get a 3D measurement using a double helical point spread function. Closed loop adaptive optical image correction is a good technique from astronomy, which can apply to flow measurement as well. So flow measurement can affect, can benefit from techniques achieved in astronomy as well. So this is the first time we applied this to flow measurement. We used the Ferrando guide star for measurement with only a single optical access. And we can get rid of the actuator if we apply a machine learning approach, in this case, a multiple interrupt neural network. Yeah, there are a lot of applications for complex microfluidic flows. So I hope I can show you that microfluidics is more complicated or more interesting than you expected. And there are a lot of flow scenarios where you can apply these techniques, and we specialize ourselves on the fuel cell techniques for the droplets. Okay, this is the end of my talk. I want to thank my Professor Jürgen Czaska. I want to thank all my collaborators, our groups, from our internal group, external cooperation partners from Germany to China and everywhere. I want to thank the technical committee for inviting me to give this talk. And yeah, I want to send my best wishes to all the people from the Ukraine. And I want to thank you for your kind attention. Thank you.
Okay, dear Lars, thank you very much for a nice invited talk presentation. So we have just a little bit of time for the questions, so I can possibly start with first question about the flickering. So is this flickering able to provide additional information about some particles, like transitional diffusion or something like that?
This is a good question. The flickering is only an apparent effect caused by the aberrations. I think there is no additional information because it's just a virtual position change, and the flow itself is laminar. So I think it's difficult.
No, but in laminar flow, you should have some transitional diffusion of particles. Means they can, you know, have a motion around the position.
Yeah, this is only a virtual movement. The particle doesn't move itself. It moves inside the water column back and forth. It might be that we can, for example, get information about the vibration. This is a case. If we observe the particles at the different heights, then we can get information about the movement, the vibration modes. This is true. Yeah.
Okay. Okay, so unfortunately we should move forward. Thank you, Lars, for the great presentation, the talk. So, and it's my great honor to introduce the next speaker, Sir Michael Berry, who will give us a talk about the 4 geometrical optical illusions. So, Michael, please, your turn now.
I can't share my screen until the previous speaker unshares.
Yes, sure. So I think it's under the way.
I stopped.
Yes, thank you. Let me try. Just a moment. Share. Now, are you seeing?
Yes, we can see
on my screen.
Yes, we can see your screen.
Very good. I'll get rid of some stuff at the bottom of the screen here. Yes, good. Well, just a moment. I have to there's too many pictures on the side of my screen. I don't know how to hide. I don't know how to. Are you seeing my screen directly? Can you hear me?
Okay.
You can hear. Very good. Well, it's of course an honor and a pleasure to participate in this meeting. And as I said the other day, I very much appreciate your courage in organizing a meeting in such difficult circumstances. Now, geometrical optics is the oldest part of our subject, and you might think that there is nothing interesting to say about it in 2023. And of course, we know it's technically enormously important in the design of and computer design and fabrication of lenses. Our spectacles, our glasses have been enormously improved in recent years by these techniques. But I'm speaking about more substantial applications within science. And I hope I will convince you that the subject is alive and well. And I will structure this talk in terms of 4 illusions, very different from each other, where geometrical optics plays a central role. Now, the first of them, let me see, is the mirage. Now, many years ago, I read a paper by very distinguished, the famous C.V. Raman, difficult person, brilliant, difficult character, and his brilliant, I think even more brilliant, but unfortunately short-lived nephew, Pancharatnam. And when I saw this paper, I immediately realized it was fundamentally wrong. And I want to explain the mistake, what they got wrong and what they got right. Now, here's the you've all seen mirages, reflections on a hot, dry road. And of course, it's an illusion. There is no water on the road. You know this. So here is the standard and correct explanation, which we mostly know. It's total reflection from hot air near the road. It's less dense than the air above, and so the light is refracted upwards. That's the basic mechanism. The rays bend towards the denser medium. The refractive index is a function of height. And so this is the locally parabolic behavior of a ray. The exact geometrical optics rule for the bending is that the curvature of a ray is the logarithmic derivative of the refractive index normal to the ray. This is a consequence of Snell's law, not very difficult to derive. Now, Raman didn't believe this. He said the theory of the mirage, which is usually accepted, purports to base itself on geometrical optics, is inadequate, unsatisfactory, and a kind of make-believe. Now, why did he think this? He had in his mind replacing the continuously varying refractive index by a stack of slabs of constant refractive index. And of course, in the limit, you would get the continuum. This was what was in his mind. And they wrote the following: a pencil of rays traveling obliquely through the medium would, according to Snell's law, be progressively deviated until it reached a layer at which its course becomes tangential to the stratifications. Thereafter, it would continue on a course parallel to the stratifications. No question of total reflection can therefore arise. Now, they didn't realize that this mistake and its correction had a long history. I found references in 1872, 1856, 1800, 1799. It's obviously wrong. It violates reversibility. And on a mechanical analogy, if you imagine throwing a ball obliquely, it would, according to his argument, continue horizontally once it reached a horizontal because it was in a region of constant gravitational potential. Of course, this analogy goes back to Isaac Newton, the trajectories of bodies which are extremely like the trajectories of rays. Now, to understand the mistake, you need to do what they should have done but didn't do in the paper, which is look more carefully at the discrete slab approximation. Slabs of thickness delta. So here's the a particular repeatedly refracted ray and totally internally reflected at one layer. Good. Well, you've got Snell's law, and I've written this in terms of the cosine, not the usual sign, and mu c critical is the refractive index where the ray would be horizontal on for the continuously varying medium. So this is Snell's law. It tells you what happens. There's a critical layer, the layer, as I said, the capital Nth, the layer within which the ray would be horizontal on the correct continuum calculation. And something really important is the following. It's where in the Nth layer is this critical height? Well, it's at some fractional height, gamma, that's the offset. There it is. And it turns out that this gamma is very important. This was unexpected. Okay, now you can easily make a local expansion and of Snell's law, and you can, it's a technicality not to be gone into now. The horizontal position of the n plus mth segment is the critical horizontal position plus a sum over all the subsequent refractions. And it's the square root of 1 over L, L labels a refraction, minus gamma. And there's this constant which depends on the slope of the refractive index and also the slab thickness. And if you replace the sum by an integral, as you think you can do when you go to the continuum limit, you then get the usual parabolic ray, which is correct. But let's see how it happens. Let's choose an offset of 1/2. Well, here you see the convergence onto the continuum parabola as you make the slabs thinner and thinner and thinner. And it works just as you would expect. The parabola is the dotted line, and here you see the individual discrete refractions. No problem. But look what happens when gamma is 0.99. In other words, where the offset is very, very close to the critical rays, very, very close to the boundary of one of the imagined stratifications. The convergence is non-uniform in gamma. Look what happens. The same sequence of ever thinner slabs, and you do get convergence onto the parabola, but it's much, much slower. Look, I've changed the scale on this picture. Here's the continuum, and you see that you converge on it very, very slowly. So Raman's near horizontal rays do exist in this model, but only when gamma is very close to 1 and with a measure that vanishes as the thickness goes to 0. So the mistake they made, they didn't make the mistake because they didn't do the analysis, but underlying their error is non-uniform convergence. So that's something, that's the solution of this problem. Now, I need to go much further. Each point on an object being mirage refracted, a distant car on the road or a tree, emits a family of rays. And a family of rays has a holistic property not possessed by any individual ray. It can form a caustic, a focal line or surface. It's the envelope of the family. Now, each ray locally is parabolic, and it's parameterized by its horizontal and vertical position of the place where it's horizontal. So you can assemble these into various different families. And one very important family is a family from a point source, a particular point on the object you're looking at that's being miraged. And here you see this caustic is a paraboloid, which is the envelope of the parabolic rays. Now, a distant scene is an extended source from which each point emits a family of rays. So an extended source is a family of families of rays, and this is important if you want to understand the mirage phenomenon, because points on the scene whose caustic is below your eye generate two images, one upright and one inverted. Points on the scene whose caustic is above your eye are not mirage reflected, no rays reach you. So points on the scene whose caustic lies on your eye are important. These points are the boundary between parts of the object that can be mirage reflected and parts which are not. And it's called the vanishing line. Well, sometimes you can have more than two images on one. Reason for that could be that the refractive index profile is not monotonic. And in Minart's book on light and color in the open air, there's a beautiful example where you see three images. This is mirage reflection from a hot wall, illuminated, heated by the sun. Now, having wrongly declared that the mirage can't be understood within geometrical optics, Raman and Pancharatnam argue correctly that it can be understood in terms of waves. And they analyze this, and it's correct, but they rediscover the Airy function of 1838, describing waves decorating caustics, and they then explore it experimentally. Again, it's correct what they do. You see, monochromatic waves in a refractive index of a stratified medium, function of height z. Here it is, the Helmholtz equation. And locally, you make a linear model where the refractive index varies linearly near the place of where the ray bends. And they studied what we now understand is a translationally invariant family of rays. And they the exact solution involves the Airy function, which we write it now in this form. It's a function of a variable, psi. It's an oscillatory integral. They understood it in terms of Bessel functions of order 1/3, but it's equivalent. And the intensity is the square. It's the squarey function. And this is the pattern that one would predict. Here's the ray caustic. And they examined this with a heated plate experimentally, and you can match very nicely to the Airy function. That's correct. By the way, one nice result I hadn't seen before, if you have a point source in 3 dimensions and you want to calculate the wave, it's the green function of the Helmholtz equation involving Airy, and here it is. I'll just show you just the technicalities I don't want to describe, except that the result is a combination of Airy functions and also the second Airy function of the second kind. That's an exact result, and it depends, and this is why I'm showing it to you, it depends on a particular rather unobvious integral. Here it is. It's a function of A and B are functions of position in the field. And this integral is this particular nice combination of Airy functions. Now, what can we conclude from this first illusion? Modeling this simple natural phenomenon involves several levels: rays, families of rays, families of rays, and waves. Geometrical optics does apply, but the continuum limit of the stack of refractive index slabs is complicated by non-uniform convergence. Misunderstanding of ray physics need not prevent construction of a correct wave description. Great scientists can make interesting mistakes, and from my knowledge of the Raman family, I have the opinion that what was wrong in the paper was Raman, and what was correct in the paper was Pancharatnam. Right. My second illusion. Oriental magic mirrors. These were first created 2,000 years ago in the Han Dynasty. They're cast and polished bronze mirrors, maybe 10 centimeters across. And the unusual feature of them is that on the back of the mirror, there's a deep cast relief pattern. Now, why are they magic? Instead of looking in the mirror, if you shine light on the mirror, you go out into the sun and shine this light on the sun shines on the mirror, and you look at the reflection of this light on a screen, on a wall, for example. You expect to see, and you do see, a circular patch. These mirrors are slightly convex, so it's a larger patch than the mirror. But the surprise, which was probably not intended by the original creators, which is why they call it magic, is that the light on the front, reflected from the front, contains a ghostly reproduction of the pattern on the back of the mirror. Now, this was a very surprising thing, and when these mirrors were brought to the West in the 19th century, there was discussion in the literature. There were papers about these magic mirrors of China and also Japan, and some speculation about how this image of what's on the back could appear by reflection from the front. And it became clear that during casting, cooling, and polishing, the pattern on the back is weakly reproduced and slightly smoothed on the front. Now, this was actually correct, but it left open the question, how exactly is the image created by these tiny curvatures on the surface, which you can't see with your eye. And I've put the word image in quotes, because if it were a normal image, it would involve focusing, and you would need to place the mirror and the screen in a particular at a particular distance. But you don't have to. It's robust over a wide range of distances between the mirror and the screen. Good. Well, you do the optics. I don't want to go through this calculation. The surface relief is imposed on the overall convexity, and you can deal with that very, very simply. I don't want to describe it. You need the magnification, and you scale. Basically, you scale the distance from between the mirror and the screen. And then you use Fermat's principle or Archimedes' law of refraction to calculate the rays. And here's what I expected, and which was wrong. I expected that caustics would be involved. This familiar regime, curvature, focuses rays onto caustics. You see this picture by painting by David Hockney, the familiar caustic in the coffee cup. No, the surfaces of magic mirrors are far gentler, and there are no caustics. Those curvatures aren't big enough. Optics is in the less familiar but simpler regime, which we called prefocal brightening. And the caustics, actually, there aren't any. They're inhibited by the gentle overall convexity, which overwhelms the little variations caused by the irregularities on the surface. So here's the result. The geometrical intensity on the screen for gentle curvatures, which is the situation with these mirrors, is, well, we call it the Laplacian image, which, if there were no undulations on the surface, plus distance times the Laplacian of the surface height variations. And we call this the Laplacian image. This is the dimensionless. So the image intensity is proportional to the mean curvature of the surface relief. Not surprising, but it hadn't appeared in any of the literature. Now, this has consequences. It has consequences when you have a surface distortion, which is in the form of a series of steps, which it is for these mirrors. Well, here's a model step. The Laplacian is a second derivative, so each step should have a bright side and a dark side. And you can test this. By the way, this is the same procedure as is used in edge detection in image processing. Well, let's take a particular step. Here it is. Smooth it vertically, and you see the bright side and the dark side. You can fit the scan to the theory, and then you can find that the height of the step is only a few hundred nanometers, which is why you can't see it. In here, the vertical scale is magnified by 16,000 times. Now, this theory works, it's correct, it explains the characteristic features of the image, but I wanted to see directly these surface variations, which you can't see with your naked eye. So I went to visit Peter Ade. He does laser profilometry for astronomical mirrors. So he uses interferometry to measure directly the surfaces. And so I took my mirror and I said, look at this part. This is the back, of course. And let's see if we can see this on the front of the mirror. Well, he put it in his apparatus. I didn't see it at all. In fact, what he saw was the overall curvature of the convex mirror. But he has clever software. He can subtract this because in astronomical mirrors, he's looking for the aberrations. And indeed, as a mirror, these magic mirrors, they're not produced very precisely, and they do have aberrations, and that's what you see. It's removing this convexity. It's the same region. Still, you don't see this distortion. And I was very disappointed, and I thought, well, maybe the theory is wrong. I don't understand it. However, he has very clever software, and he can progressively subtract higher and higher order polynomials fits. And when you subtract a 9th order polynomial, then at last you see these surface distortions, and you can measure them, and for the particular scan across here, the variations are about 1 micron. So this is correct, and it confirms our understanding. Well, a more recent development is with David Jessen, Howard Snelling, and Anton Surkov, is there a refraction analog? Can you make magic windows? Well, it's the same theory. Refractive index n, it replaces the -1, which is the refractive index of a mirror, and it's the same. So then you could ask this: how do you form a surface to produce a particular image by transmission? Well, you have to solve Poisson's equations. Here's your desired image, and to find the height, you solve Poisson's equation. Well, there do exist some similar objects, but they're not magic windows. They're windows where you can actually see the variations of the surface. Matthew Brand at MIT, here's a window, the sun shines and you produce this on the ground, and Mark Pauli in Lausanne makes similar structures, but magic. Well, here's my grandson, and I put him on the right-hand side of Poisson's equation, and this is the greatly magnified, the surface relief, which would transmit an image which would reproduce him. And you, on the computer, you can very quickly calculate the Laplacian, and of course it works. You get a pixelated version. In order to publish this, I had to get ethical permission from my daughter to publish this picture of her son in the journal. This is the way crazy things are nowadays. Well, progress so far in creating a magic window. Well, first of all, to see that the transmission theory works, you can take an existing existing mirror. Here's the reflection from theirs, and you can cast plastic polydimethyl siloxane perspex on the surface, and then get a cast, and then you can look at the transmission through that, and it really works. So we know the transmission theory works, but we want to produce a predetermined image, not an image which comes from an existing mirror. And they chose, this is, by the way, not trivial. It's a kind of free-form optics, but the regime where the horizontal scales are millimeters and the vertical scales are microns or fractions of a micron is apparently very difficult. This is what those people in Hull, my colleagues who work on glass formation, tell me. And they invented a technique, I won't describe the details of it, and their city, Hull, was a city of culture for 1 year, and this was the logo. So they decided they would make a magic window to reproduce this. Here's the Poisson transform, the function whose Laplacian is this shape, and they could create it experimentally. And this is the image that they hoped to get, and they did get it. The only problem is it's actually very small. It's only about ½ centimeter. And what I wanted is a big magic window, and they're working on this now. Now comes the third of my illusions. I'm rather ashamed that I lived for more than 70 years before I had learned about this illusion, but I'll describe it. Many of you might have seen it. In my experience, most people haven't noticed it. Well, we know that the sun lights up the moon. Therefore, you would expect that when the sun and the moon are in the sky at the same time, the lit face of the moon should point towards the sun. Well, it doesn't. Here's the moon, very small, but you can resolve it, and this is the direction where you would expect the sun to be, but here's where the sun is. Well, it's not easy to photograph this, by the way. The moon is much smaller than you think. It's 1/100,000th of the area of the hemisphere of the sky. When, of course, you take a photograph of the moon, you zoom in, that's easy. But if you want the moon and the sun and they're widely separated, which is when you see this phenomenon, then it involves, you have to be a little bit careful. This is my smartphone. I was able to do it. Well, it is a geometrical illusion because, of course, the lit face of the moon does point towards the sun. Here's the sun, here's the moon, here's the lit face. But we don't see this view. We're on the Earth and we see directions. And we see these celestial objects on the direction sphere. Now, on the direction sphere, the line between the moon and the sun is a geodesic. There it is. Now, when you look at the sky, you don't actually see a hemisphere. You see something, well, it isn't quite clear what you see, but it's something more like a screen, but not exactly flat. It's a perception and image dependent sky view. And you know from geography that almost every representation of a sphere, the geodesics are not straight lines anymore. You see this from common maps of the Earth's surface. And I wanted to study this precisely. And one way to study it precisely, where you know exactly what the projection is to use a witch ball. Here is a witch ball. It's a perfectly reflecting sphere. I have several of them. And when you look through them, you can see, or you can look horizontally, or you can look vertically, and you can see the whole 4 pi of directions on a disk. On the edge, you see what's almost in front of you. In the middle, you see what's almost behind you. You see the whole 4 pi of directions. They're called witch balls in the UK because there was a story that they used to be hung in the windows of country houses. So if a witch would approach, she would see her reflection from whichever direction she came, be afraid, and fly away again. Okay. Well, one knows what the mapping is. Directions are represented by points on the disk, radius r. Light from direction theta with relative to backwards appears to come from points r sine a half theta from the center of the disk. Very well, then you can simulate everything because in the sky, you would then see the moon, squint moon illusion as on the disk, and you can calculate exactly what the distortions are. So here's a typical view you can calculate. This is the attitude vector where you expect the sun to be. Here's the horizon, here's the zenith, here's your viewing axis, here's the geodesic, and here's the direction where you see the sun, the apparent direction. And of course, the squint angle can be calculated. So you can solve this whole problem, and you can make a variety of different simulations. You can look up, which is looking down in the witch ball. You can look obliquely, you can look horizontally. And apart from a few special cases, almost always the sun does not appear to be where you think it should if you look at the direction normal to the face of the moon. Now, an interesting aspect of this problem is that at full moon, there's a discontinuity, because at full moon, you can't tell which side is illuminated. Indeed, as you pass through full moon, the illuminated side jumps from one side to the other. So this is an antipodal to the sun singularity in the pattern of these attitude vectors. There are singularities of index +1. So that's a nice feature of the geometry of this problem. Well, before I got my smartphone, I had an old-fashioned camera, and I went out one day in Bristol at a time when the sun was nearly setting, but the moon was in the sky, tiny, tiny moon image. And you could zoom in, and you can see the direction of the lit face of the moon, and here it is. And it's not the direction where the sun is. Here's the geodesic. So this theory works, and it's it's a nice application of geometry in the presence of curvature. Very good. Finally, distorted and disrupted reflections. Let me show you an illusion. I'll introduce my wife. Here she is. Of course, it is an illusion. She doesn't look exactly like this, and there's only one of her, not three, and they don't merge and disappear. Well, to produce this picture, I took a sheet of flexible polyester, which I bent it in such a way that it's convex in some places, convex in the other. She stood above, looking down, fixed, and I moved the camera horizontally, slowly and continuously, and recorded the picture. And I wanted to understand the anatomy of these reflections. By the way, they're very, very common. This was on the London Underground train, looking in one of the curved windows a few weeks ago. If you look in curved fairground mirrors or the curved metal on the sides of cars, you see these distortions all the time. And not only distortions, but more interestingly, topological disruptions. And I want to understand what's happening. Well, you have an object, for example, my wife's face. And you have a mirror, which is not flat, and you have an observation plane, which could be the same as yours, it doesn't matter. And here's your eye. You are looking down at points R dashed, and so you see the points from which rays are reflected specularly into your eye. And you can it's essentially paraxial optics, and you can do the calculations explicitly. And there's an interesting, beautiful answer for what you see. If you have an object whose intensity is I0 as a function of position in its plane, for example, my wife's face, the intensity that you see looking in the mirror at the place R prime is given by an explicit formula. And I'll make a point that in much work involving these reflections, you have to deal with inverse functions. Well, here you don't. Here's where your eye is, here's where you're looking at, and here's the height variation, height function of your mirror. Now, one important feature, if the point where you're looking at is on a caustic of the family of rays from a particular point R0, the determinant vanishes. This is reflection. This is focusing. A lot goes into a little. There's 0d rho and finite d r dashed. Then this is infinite magnification of this particular object point, because essentially dr dashed is infinite, and if you don't move your eye, d rho is 0. This is well known, for example, in gravitational lensing. It's this infinite magnification of points associated with caustics is a part of the understanding of images of distant objects as distorted by gravitational lensing from intermediate objects, which could, for example, be dark matter. Now, astronomers can calculate these distortions, but they don't understand or don't need to understand the anatomy of these distortions and disruptions, and this is what I want to finish by describing. You can think of an object as a collection of curves, for example, contours of intensity. Each point on a curve emits a family of rays. We saw this earlier. So each curve corresponds to a family of families. You ask, what is its shape when you view it by reflection? Well, it's distorted, but it can be disrupted topologically. And there's a theorem. Topological disruption is occurring when light emitted from your eye in the old Greek fashion, light rays from the eye get reflected into the region where the object curve is. And when the caustic of this false light touches the curve that you're looking at, then the image of that curve will be topologically disrupted. You're familiar with these. Here's the mast of a ship above here. Here's its distorted reflection, but also disrupted. There are these loops off to the side. Now, an object is a collection of curves. So an object is a family of families of families of rays. And here's the key point. As you move your viewing, your eye, images of different curves change their topology at different times. And this underlies all of the strange images that you get. And I just want to illustrate this just to show you a series of pictures where you look at caustics of different types as classified by catastrophe theory. This is the geometrical classification of stable caustics produced by, well, in this particular case, mirrors of different local topography. Well, the simplest is pictures of me. Here's the simplest singularity, where you go from 0 images to 2 images. This would be a cubic mirror, and here you go as you go across from no images to 2. Well, the cusp, you go more complicated, even additional parameter, you go from 1 to 3, and you can do it in several different ways. Here you have 1, here you have 1, here you have 3, here's the 3. The swallowtail, more complicated still, is an additional parameter, and you can go between 0 and 2 and 4, or 0 and 2, depending on, this is a caustic that lives as a surface in 3 dimensions, if you understand it geometrically. Well, here you are, you see the different parameters, and indeed, you can see 4 images. Well, this looks straightforward, but it's much more interesting when you have mirrors that are curved in 2 directions, not just curved in 1, like fairground mirrors, and as the cases I've just described. These are the so-called cuspoid catastrophes. But if you go mirrors that are curved in 2 dimensions, you get much more interesting, beautiful shapes. Well, here, this is called the elliptic umbilic singularity. You go from 2 to 4, and this can happen in various different ways. There are 3 parameters involved, and you get a very interesting, unexpected images. Here they are. These images are computed, of course. It'd be interesting to fabricate surfaces according to these prescriptions and look and then look experimentally, but they do correspond to many of these distortions that one observes. And then finally, the other singularity, which has codimension 3, you have the hyperbolic umbilic, and here are some of the shapes that you see. Here's you see the 4, and here you see a different shape, and here you see another. So weird and wonderful distortions, all of which are organized in the way that I've described, where you have to go beyond the imaging and focusing of points to the imaging and focusing of extended objects, and then you get different geometrical considerations are involved. Well, these are my illusions, and I've written about them in a series of papers. They're all on my homepage, published all this century. So, as I said, geometrical optics is alive and well, and I've illustrated it in terms of these 4 illusions. So with that, I thank you very much for your attention.
Thank you very much for such an inspiring invited lecture. So, and we have just a short time for a few questions. Any questions, please? Yeah, please, Etienne.
So, so thank you, Michael. I've got a quick question. Obviously this is an unusual form of imaging, the Laplacian imaging that you talk about in the magic mirrors. Do you have any examples of where that sort of imaging is used in nature, say the natural world, but in the eyes of some sort of organism?
not eyes of organisms, but sometimes, and this has happened, where if you're in a room where the window consists of very old glass, the glass gets distorted with age. Now, you don't notice this when you look through it and see what's outside, but sometimes in the morning or evening when the sun is shining in, you can see these distortions on the wall behind, and then they're not caustics because the distortions aren't strong enough. But you see essentially these.
No, they're straight lines rather than curved lines. I've seen it.
Yeah. So you see these different. It's not speckled because it's not interference, but you do. It's something like that, and you're seeing the Laplacian of the variations of the thickness of the lens. It's not exactly nature, but it's it occurs in a sense without our intervention.
One might have noticed it in everyday life.
That's right.
Yeah.
Now it's really rather surprising that this very simple Laplacian regime, it's actually simplest beyond beyond perfect transmission, isn't widely discussed. But in electron microscopy of thin films, it was discussed, and they didn't use the term Laplacian image, but it's essentially the Laplacian that determines the intensity of electron microscope images. And indeed, the reason why I went to study these magic windows was David Jesson, who was an electron microscopist in Cardiff, had used my paper on the magic mirror from some years before to interpret electron microscopy, explicitly using the Laplacian, and it turned out this had gone back a number of decades within electron microscopy theory. So that's just sort of tangential response to your question. Thank you very much.
Thank you.
And we have another question from Professor Igor Mokhon. Igor, please.
Very simple questions. Can you propose more practical application of your illusions, expecting art and so on?
The people who I mentioned, who have created windows that are not magic in the sense that you can see the distortions, but which nevertheless produce rather beautiful predetermined transmission structures, are associated with architects as a way of creating windows in modern buildings, which when the sun is in particular positions, will cast unexpected, interesting images on walls inside the structure. So they call them caustics. They're not caustics, but they misapply the term. But it's essentially these images from distortions which, well, you can see the distortions with your eyes, but in a big window, this wouldn't be obvious. But so this is a sort of aesthetic archaeology. So that's one recent application. Others I'm not aware of, but I'm sure there must be many. But it's a good question. Thank you.
Thank you.
So, okay, unfortunately, we should follow the timetable of the conference, and we should move forward. Thank you very much for this great talk.
I have to catch a train, an international train now, so goodbye. Thank you.
Yeah, thank you. Bye. So, and we're coming to the last talk to this morning session. I mean, the first part of that, so which will be given by Masajida?
Agnieszka.
Agnieszka, okay.
Agnieszka.
Yeah. They say I assume you're from Poland, but on my track record there is not mentioned your university. So, but please,
Okay. So I will tell.
Get the flow. Yeah.
Yeah. I try to.
And the talk will be about vortex quadrupole trajectories sitting in a Gaussian beam.
Yeah, that's correct. I will switch to the presentation mode. Okay. Oh, it's not working. Okay. Can you see my computer, my screen?
Yes, yes, we can see you.
Okay.
We can hear you well.
Thank you, Chairman, for the introduction, and I would like also to thank organizing committee for giving me opportunity to present my research. The title of the presentation is Vortex Quadrupole Trajectory Seeded in the Gaussian Beam. My name is Agnieszka Popiołek-Masajada. I am from Wrocław University of Science and Technology in Poland. Two other co-authors are also from the same university, Markevich and Jan Masajada. And we did this work with cooperation with Albert Ferrando from University of Valencia in Spain and Anna Khoroshun from Faculty of Computer Science and Engineering, now in this university, moved to Kiev in Ukraine. But before I will talk about this particular topic, I would like to say about our motivation, which caused that we started to deal with this problem. In 2022, I was involved in the implementation project, which was entitled Development and Construction of the System Enabling Real-Time 3D Visualization of the Football Matches. And one of the scientific topic or task there was to improve the concept of calibration system of masts, cameras, and lenses. And the idea was that 12 masts with different type of cameras will be situated around the football pitch, and they needed an adjustment or positioning relative to each other. The masts were separated by the distance of hundreds of meters, and the environment between them was the atmosphere that can have a different temperature between this mass, or the same different refractive index that of course will disturb the propagation of the beam, the propagated beam. So we proposed to add the internal markers, optical vortices, into the Gaussian beam, which was transmitted through the whole pitch, football pitch, and we expected to improve the beam positioning. In this way, having a well-defined and stable singular points, they can within the laser beam, they can serve as a position markers. And when we did the literature research, we found that some papers stated that vortex beam offers some additional benefits over a pure Gaussian beam, being more resistant to random inhomogeneities in the atmospheric refractive index. So we wanted to test this hypothesis and whether it can be used in this particular situation. And during the study, we considered propagation of four beams. First was the Gaussian, the pure Gaussian beam. The second was the beam with the vortex of topological charge equal to 1. And then the third was the beam with topological charge equal to 4. And it is known fact that such a higher order vortex beams are unstable, and then under any perturbation, they split into the set of single charge vortices. So in a far field, in fact, we will observe 4 separated dark spots. And finally, we wanted to test also the quadrupole vortex beam. And here, similar as in the electric case, it consists of alternating positive and negative charges arranged on the corner of the square. And we expected maybe that such an arrangement will possess some features that will stabilize even more that beam. And we performed numerical simulation and also experimental measurements, and the results were published last year in Optics Express paper, and I will show only the experimental results to not prolong the presentation. We propagated the beam with this internal structure I mentioned earlier over the distance of 100 meters through the induced turbulence. It was a ball with a hot water. And the beam was focused, and on the CCD camera, we observed the sequence of images, this laser spot, and then analyzed. And when we look at the Gaussian beam, when it goes through the turbulent media, this turbulence randomly deforms the beam shape and intensity distribution within the beam. And you can observe this on this movie, which is here. And then beam position is found using the center of gravity algorithm that calculates the weighted centroid position. Under the turbulence, in our experiment, the beam center was dispersed over the 40 or 50 pixels. When we, in case of the vortex beam, when this beam passed through the turbulent media, the turbulence also randomly deforms the beam shape, and additionally, it also shifts this dark point within the beam. And here, to find the beam position, we trace the dark spot instead of inspecting the whole beam. And then experimental results showed that finding the beam position in the turbulent condition was less dispersed compared to the Gaussian beam by a dozen of pixels. So we have on the slide here, we can compare the beam positioning with this pure Gaussian beam and with vortex beam. And here this dispersion of results is much less in case of the vortex beam. And when we apply the higher order vortex beam with topological charge equal to 4, then it was split into the 4 separate vortices. The turbulence also deforms the beam shape and also changes the distances between the separate vortices, because each vortex passes through another or different media. So to trace the beam or to look for the beam position, we can look for the centroid position, and then we found that this beam, the dispersion or finding the position by tracing the center of gravity, the centroid of these 4 points is less dispersed even than the single vortex charge beam. And we wanted also to apply the quadrupole within our beam to test how it behaves. And we found during the experiment that the intensity images that we obtained were completely different than from the expected. The appearance of the spot strongly depended on the quadrupole size. And that was the reason that we started to study this, the propagation of such a quadrupole beam more systematically. And to do this, we asked Albert Ferrando from University of Valencia in Spain, because he had worked out the algorithm or procedures which allow to trace or to propagate the multisingular beam by the means of scattering modes. This his procedure or his algorithm was described in the paper shown here, and we got some progress in this work. So I will show briefly how this beam behaves or how this beam propagates. It is well known that the complex amplitude of the optical field verifies the paraxial wave equation, which is written here. Multi-singular beams contains a set of positive and negative single charge phase singularities. Its complex amplitude can be, in the most general case, can be written by the equation shown here, where W and W slash are complex coordinates. Phi 0, 0 is fundamental Gaussian modes. And this part here indicated by blue represents a set of positive charge vortices at the position A, And this marked by this red color represents a set of negative optical vortices situated at the position within the beam. Multisingular Gaussian beam can be expressed also in the polynomial form. So we have a certain polynomial p multiplied by the Gaussian function phi 0, 0. P is a general complex polynomial in order of and plus and then minus, and it is expressed by the certain coefficients t that are obtained after solving the paraxial equation. And when we have the form of this polynomial, we can look for the zero of this polynomial to find the position of the vortex within the beam. And the zeros of this polynomial at every z will determine us the trajectories of the phase singularity. And this, because these are dark points, these trajectories are the dark rays since the intensity vanishes there along them. Okay, so in this particular arrangement, so let's introduce this particular arrangement of the quadrupole. So we have a positive and negative and positive sign. They are displaced by the distance d between them and by the distance a from the beam center. The results are normalized to the wavelength, and from the initial conditions at the beam waist, we can obtain the starting form of the polynomial, and then when we propagate it further, so the global solution is in that form, which is shown here. And finding zeros of this polynomial determines the non-trivial trajectories of the phase singularities in terms of the z of the propagation distance. And the presence of the vortex pair in this beam causes its annihilation or creation. So therefore, by analyzing the number of points that are created or annihilated, we can, in terms of the dimensional length ratio, W0 over the D, because this polynomial depends on the parameters A, which is somehow the distance, the size of this quadrupole, and Z, ZR value, which can be recalculated to the beam size. We can classify quadrupole vortex in only 3 equivalent classes. And the class number 1, the first class, is characterized by the number and p equal to 6. And we can see on this slide here the intensity pictures of this quadrupole beam when it propagates in the near field. So here we start from the beam waist, and here is the positive z direction propagation. And we can see that this initial arrangement is somehow disturbed, that these vortex pairs are coming closer and they disappear, forming a kind of a loop in the near field. When we move further, then we can see that this central quadrupole is created again in the central part, and additionally appears a set of 2 vortex pair branches within the beam. And when we look at the dark beam trajectories, in this case of class 1, we can plot it in this way. So we have here the central part, the central beam, around the beam waist. Here this loop is formed. So we start from the arrangement of the vortex quadrupole, and then when we move in the positive z direction, they annihilate, and then at a certain distance, they are recreated again, with the additional branch of vortex pairs. So 2 pairs annihilate in the near field, and 4 pairs are created in the far field. So the number and p here we can call equal to 6. The second class looks like that when we look at the intensity pictures. So we start if we start from the beam waist, we can see that the central quadrupole does not disappear, but at a certain distance it appears additional branch of the optical vortex, and therefore the number is equal to 2 because of this additional part that are created because there are 2 pairs of the vortex pairs created in the far field. And the global picture of this dark rays is plotted here. So again, we start from the beam waist with the initial arrangement of the optical with the vortex quadrupole. We do not observe the central loop, so the vortices here do not disappear, and these additional branches, 2 additional branches of vortex pair are created, giving the number of NP equal to 2. And the third class is characterized by the NP number equal to 4. And here again, in the central part, we have a loop. Starting from the beam waist, we observe the vortex, the central vortex disappearing, and going to the far field, we observe that they are recreated and no additional vortex pair are generated in this case. And in this picture here, we can see the dark rays trajectories here. So the central loop and the recreation of the vortex pair in the far field. Therefore, we have an NP number equal to 4. So 2 are annihilated and 2 are created in the far field. These classes depends only on the dimensionless parameter, as I said before, delta that is equal to beam size divided by the quadrupole size. And in terms of this forward propagation from z equal to 0 from the beam waist, class 1 and 3 exhibits annihilation of the original 2 pairs at the actual distance, followed by the propagation with no singularities. So we have this loop until generation of 1 in the class 3 or 2 branches of vortex pair in the far field. And contrarily, in class 2, the original 2 pairs never annihilates, and only 2 new outer pairs are created at further z distances. As the quadrupole arrangement possesses intricate dynamics, it raises the question whether the different classes of this quadrupole structures are stable or not under perturbation of initial conditions. And from the experimental point of view, a dark beam stability is closely linked to the tolerance of the optical beam features under misalignment. So we studied the evolution of the beam trajectories when the initial condition is perturbed by randomly moving the phase singularities from their symmetric position for a given class. And we can tell that the dark beam structure will be stable if the number of points and where the pairs are created or annihilated for a given class remains unchanged under perturbation of reasonable strength. And here are the exemplary results. Here we show the results obtained by a perturbation of the initial condition of class 1 of our quadrupole vortex beam. The perturbation consists of modifying the position of the singularities at the beam waist with respect to their original symmetric locations. And this is done by adding a random complex number at every singularity location and analytically calculating the resulting perturbed beams by means of the same technique. And the results showed that the curves the vortex points are deformed with respect to the symmetric case, but the pairs are annihilated and created at exactly 6 points, as in the symmetric case. So the dark beam structure is no longer symmetric, but the number, the class remains invariant. And our theoretical results were verified experimentally. We used the experimental setup that consists of a special late modulator at which we displayed this quadrupole structure. The Fresnel lens was added here to observe this focusing area of the beam. A reference mirror was added to observe also the interference fringes at which we can see whether the vortex is present or not in our beam. And the CCD camera was moved along the z-axis to determine the vortex trajectory. To find the vortex position, we applied the vortex filtering technique together with the specially trained neural network. In this procedure, regions of low intensity were preliminarily identified and extracted. To extracted images, it should be 4, each containing a vortex. Vortex filtering was applied, and on the pseudo phase mask, spiral geometry then is visible. We used a specially trained neural network that localized the end of the spiral, showing the vortex position, and vortex position here is indicated by the circle, and we've also found the centroid position that show us the beam center. And the results of the experiment are presented here. Here, the beam propagating along the z-axis. In front of this beam waist, we can observe the four dark area, and the vortices are presented here. When we move further, we observe this annihilation. The fork fringes disappear, and when we move even further in the positive z direction, we observe the recreation of the optical vortex, which is confirmed also by the fork fringes on this interferogram. When we look at the trajectories on the projections, so we can clearly see that they, with moving the z position, they are getting closer and closer and annihilate, and they are recreated again. And another characteristic feature that appears during the quadrupole propagation is formation of the additional branch of vortex-anti-vortex pair. To observe it, we change a little bit the beam side, the beam laser. The beam laser was expanded, the beam laser divergence, and then we could observe the central quadrupole. Sorry. The central quadrupole and also the additional branch of the vortex that are created within this beam. So to come to the conclusions, we investigated the propagation of the Gaussian beam with the embedded two vortex pairs. Such configuration exhibit rich behavior that can be controlled by the manner of the beam size and the beam quadrupole. The vortex pair can annihilate or create. Creation and annihilation of vortex pairs during the beam propagation can be controlled by a single parameter that is related to the vortex quadrupole size versus the Gaussian beam waist. 3 different classes of the vortex trajectories can be identified on the base of the number of created or annihilated vortex pair. And we have also shown that the vortex trajectory pattern is resistant against the small deviation from perfect initial parameters, which makes them possible to detect in the experimental conditions. And I would like to thank you for your attention.
Okay, thank you, Agnieszka, for a nice presentation. So, and the presentation is open for discussion. And we have a first question from Mark Dennis. Mark, please.
Hi, Agnieszka. Thank you very much for a very interesting talk. So,
hey, hi.
Hi. So, what you were talking, this configuration you're studying here is very similar to the simplest situation that we looked at when we were looking at optical vortex knots. In fact, a pair of linked rings would be possible with just 4. And we found, in our studies of this, we found exactly what you're talking about, that we had to get exactly to make sure that we had the linked rings, like your single ring without it going off to infinity. We needed to get the balance with the beam waist exactly right in the same way you're talking about. So my question is, did you ever see anything that looked like a link of your 4 vortices, or did you only saw a single ring in that regime? I can't remember which number it was.
This ring can be observed probably maybe in this area of beam when the beam is focused, but it is hard to get into this to experiment in experimental conditions. Yes.
Yeah. So I mean, but you only saw a single ring. You didn't find a different regime. So I think so I can say the link that we looked at, rather than having the vortices on a sort of rectangle, they were all collinear. So if you have something like plus, minus, minus, plus, collinear, something like that, or if you move towards that, you might find this linked ring topology that we found. And so it might be interesting to see how you go from the quadrupole giving you a single loop to giving you sort of a pair of rings. So I think that sounds really that's really interesting. That's not something
maybe we can make it more complex to add the pair. On the SLM we can display many different configuration of vortex pairs, and then we can look for these links. But
exactly, but I would say try them being collinear, but with the plus, minus, minus, plus is important to have that as the array of charges. But I'm happy if you want to send me some emails. I'm happy to discuss this further. I think it's really interesting.
Thank you.
Okay, thank you, Mark. So, and we have the next question from Professor Khoroshun.
Thank you very much for the nice report. If I understood correctly, you use the paraxial approximation in your calculation, theoretical, but simultaneously you say about the near field, and maybe we have some contradiction here. Can you comment?
I must say that I was responsible for this experimental part. Yeah, so Albert was doing this theoretical calculations. By near field, we mean where we are at the beam waist. Yeah.
I see. Thank you.
Dear colleagues, I'm sorry, we need to stop our discussion because we have one presentation by Professor Wang during the coffee break. That is, I'm sorry, all questions in the chat, please.
Okay, thank you, Claudio. So, and I then can I pass then my chair duties to other chair, Professor
Brasselet, but I invite Professor Wang because here we skipped his presentation 2 days ago, and now I would like to invite him to present, and then we continue with Professor Hanson according to our timetable.
No, that's fine, but I'm saying that I pass my chair duties to other chair of the session, Professor Etienne Brasselet. Etienne, please.
Okay.
Hello, can you hear me, everyone?
Okay, yes.
Okay, good. Good morning, everyone. Good morning, everyone, and it's nice to see every old friends in this conference. Okay, first of all, I would like to thank the conference chair for the invitation. And in this Monday, okay, I have some kind of personal accident, so that I cannot give the presentation. So now I come back and just present our recent work. As shown in this title, today I would like to talk about towards the diagnostic for random polarization. How Stokes correlation provide information content of the stochastic optical field. Here shows the co-works of with piece of paper. Okay, I'm from Herrod University, and Professor Hanson is from DTU Electoral of Denmark, and Professor Takeda is from Utsunomiya University of Japan. Here shows the outline of today's talk. First, I would like to just introduce, some kind of basic concepts about the random polarization, especially referred as the polarization speckle. Therefore, we would like to introduce how to start from the scalar speckle to polarization speckle. Then we will change to the concept of the time averaging, and it's compared with the ensemble average when applied for study the polarization speckle. And the next one, I will just give the brief introduction about the autocorrelation function and the power spectral densities of Stokes parameter. As you know, this conference, this series of conference is focused on the correlation optics. So therefore, let's say in this talk, we would like to, to enhance how the correlation of Stokes parameter plays an important role, to study the polarization speckle. Then next, we'll move to the statistics of the integrated Stokes parameters. Okay, and in this second part, I will introduce the means and the variance of the integrated Stokes parameters, and introduce a new concept referred to as the numbers of degrees of freedom for Stokes detection. And the next one, we will move to the approximated probability density function of the integrated Stokes parameter. So, and once again, so we will just try to explain why autocorrelation of Stokes parameter plays an important role for detection of the random polarization. In the third part, I will introduce another new topic or new technique referred to as the Stokes vector interferometer. So through the cross covariance matrix of the Stokes parameter, we try to reconstruct or retrieve the information content of the stochastic optical field, and how does it works for this kind of new interferometry. Okay. First, okay, let's move to the fundamental concepts related to the polarization speckle. Polarization speckle is ubiquitous, okay, as you see in this figure. Okay, if we shine a light, okay, laser to an object with a rough surface, we can easily observe a granular structure referred to as the speckle phenomenon. Okay, this is well known. Okay, even the incident light, okay, is linear polarized or is perfectly polarized after scattering. The scattered light, will have not only the random intensity, okay, as the right side field, but also the polarization state also may be random. So therefore, the polarization speckle manifests itself as a random spatial variation of the state of polarization and the intensity, with their Stokes parameters varying in random way across the whole pattern. Okay. So right side figure shows a typical pattern for the polarization speckle. And the statistical properties of polarization speckle have come to attract the new interest, because this type of phenomena, have a very wide connection, and applications in the practical field, such as biological imaging or optical metrology, and some kind of astronomical, observations. And this figure, shows just an intuitive way to explain the generation of polarization speckle. So polarization speckle is a random electronic magnetic field generated from the coherent superposition of multiple, random vector field, sometimes referred to as the polarization phasor. Okay, through the random work, okay, we are able to, generate to understand the polarization speckle in this, intuitive way. And here shows the general just mathematical representation of the random work for the polarization speckle. Okay, as you see, for each component, X and Y polarization component, that is from the superposition of many coherent phasors, okay, together. So finally, we will have the polarization speckle of for the random stochastic vector. let's say, as you see from the left side figure, okay, we can also easily generate just a perfect polarization speckle through shining continuous wave laser through just a rough surface wave, just a wave plate or rough surface birefringent material. Okay, because of the birefringence of the material itself, okay, even the incident light is perfectly polarized after scattering. Okay, we can easily generate this random polarization speckle with random polarization state. And the right side figure shows a typical patterns for this polarization speckle, as you see. And at the different locations, we have a different intensity, and also the state of polarization are also different. And since the incident light is from the ideally stabilized continuous wave laser. Okay, so the scatter field itself is also stationary. Okay, so for this reason, we can use this analytic signal to represent the scattered field just behind this depolarizing diffuser. Just behind this one, we can use this analytic signal for its mathematical representation. Since we have this analytic signal for this electric field, okay, we are able to study, at least theoretically study the polarization properties and the coherence properties. Okay, as you see, to represent the polarization property, okay, the most important quantity is called the polarization matrix, which is defined as the coordinate product of the electric field vector itself. So since based on the convention or definition on the time average, we can easily see that after time average, the time dependence of the electric field disappear. So therefore, in the polarization matrix, okay, it is only become the space dependent matrix. Okay, and based on the definition for the degree of polarization, okay, we can see that here for this type of optical field, the degree of polarization under the base of time average is equal to 0 at everywhere. So therefore, through this kind of conventional definition, we see that the degree of polarization for the polarizing speckle is always unity. So it means that the let's say this polarization speckle is fully polarized everywhere. Now, okay, with just besides the polarization property, okay, the coherence property is another important properties related to the statistical optical field. Okay, and right side figure shows a typical way, for coherence, detection. Okay, if for let's say if we have the optic field, okay, if we are able to connect the optical field through the fibers, and then make the interference. Okay, we can just we can just measure the optical coherence of this field through the through the fringe contrast, through the fringe contrast. And since let's say after this depolarizing diffuser, okay, we have this analytic signal just behind this diffuser. Okay, we can also substitute these equations to the definitions for the mutual coherence matrix. Okay, gamma. Here, gamma is a mutual coherence matrix. Through its definition, okay, once again, here, this represents the time average. Through the time average, we see that now the mutual coherence matrix has been reduced to this form. Once again, here, the time does not involved in this kind of phenomena because the field itself is perfectly, just stationary. So, and once, if we use, let's say, if we make, give introduce the Frobenius norm to this mutual coherence matrix and give it just a normalization, okay, we are able to get this small gamma. Small gamma is also a matrix. And it is quite natural to see that the Frobenius, the norm for this small gamma is always become 0 everywhere. So once again, the degree of coherence for the polarization speckle is always unity. So through this slide and the previous slides, we find that the polarization speckle is completely polarized and fully just coherent field. Okay, so in this sense, the conventional definitions or conventional concepts of degree of polarization and the degree of coherence, based on the time average, cannot be directly applied to this particular, stochastic optical field. Therefore, we should to consider that what is the best way to describe this, stochastic optical field. Here, rather than averaging with respect to time, instead we average over the ensembles of different birefringent polarization scrambles. So it means that, okay, so here this ensemble of the ensemble of polarization speckle will be generated, by changing a lot of the birefringent polarization scrambler, okay, or by changing the a lot of just diffuser, depolarizing diffuser. Okay, all these depolarizing diffusers has the similar statistical behaviors with its similar microscopic structure, with the same orientation for the first axis, and also with the same birefringent refractive indexes for these birefringent materials. So all this under this kind of ensemble average concept, okay, we can apply, we can just make use of the similar mathematics, but the ensemble will be applied to this definition. So through this way, okay, we can just introduce one set of polarization matrix and mutual coherence matrix like this way, under the ensemble average. And based on the same mathematical, expression, the similar, the degree of polarization and the degree of coherence can also be introduced in a similar way. Here, oval bar represent the ensemble average, not the time average. Okay. So once we have this, introduce this ensemble average, definition for the polarization speckle, okay, we can just, apply this ensemble average defined as a concept to study the polarization, speckle phenomena. Now, here just show you some, the distinctions between these newly introduced concepts. Okay, as we know that for the conventional degree of polarization defined, okay, on the base of time average, okay, the degree of polarization represents the amount of polarized components as compared with the total amount of light. Okay, total amount of light. So this concept was originally proposed by Professor Emil Wolf and has been widely used, and achieved great success for the some light from the thermal light source. Okay, but here once we apply the ensemble average, okay, okay, we can see that this degree of ensemble average polarization has a completely different physical concept as compared with the conventional one defined on the time average. Here shows just two speckle patterns. As you see, from the right side pattern, okay, the state of polarization are most, concentrated with the horizontal linear polarization. So it means that from the ground plane sphere, okay, we can see that they are most concentrated, along the axis of S1 axis, okay, represents the, the S1 axis represents the linear polarization along the horizontal direction, okay. And the right side figure shows another pattern for the polarization speckle, as you see. Okay, so here in this pattern, okay, we can observe a lot of different, state of polarization. Some at a different position. Some position we have the, we have the linear polarization, and some position we have the elliptical polarization, and some have the circular polarization. So in this sense, okay, as you see from this, the corresponding point plate sphere, okay, this point plate sphere has been uniformly distributed of all the points, represent, this different state of polarization. So through these just two figures, we can see that the newly introduced degree of ensemble average polarization, okay, serves as a measure of the spatial randomness of polarization state, although the field itself are fully polarized everywhere, everywhere. So here, random polarization, here, the degree of ensemble average, it gives a different, physical indication as compared with the conventional, degree of polarization based on the time average. Now let's move on to the, let's say, the newly introduced degree of ensemble average coherence. Okay. As we know that, for the thermolite, the conventional definition for the degree of coherence, okay, indicates the ability of light field, okay, at the two positions to generate, to interference with each other for fringe generation. So therefore, through the fringe contrast, okay, we can just make a judgment the degree of polarizations from the fringe contrast. Okay, so therefore, the based on this, that is the definition of the well-known definition for the degree of coherence based on the time average. But here, okay, as we just explained before, for the polarization speckle everywhere, okay, is fully coherent. So if we just make a, interference, Young's interference at any two locations, we can always observe a clear fringe pattern with the high fringe contrast. So what is the concept, or what is the indication of the degree of ensemble average coherence? So as you see these figures here shows this just the definitions or just physical indications of the degree of ensemble average coherence. So degree of ensemble average coherence serves as a measure of spatial correlation of random signals from fully coherent optical field. Okay, so even the spectral field is fully coherent. So here, this degree of spatial average coherence is a kind of an indication of the spatial correlation. So as you see from the first the left figure, okay, so it means that these two random signals, okay, are fully mostly uncorrelated, let's say, partially correlated. And the right side field shows some, the random signal which are fully correlated to each other. So from which each positions, we can always predict, the different locations. Even the signal itself are random. So therefore, here the degree of ensemble average coherence, just gives a completely different, physical indication as compared with the conventional definition based on the time average. So once we have this these two two degrees based on the ensemble average, now okay, we can apply these two concepts, to study the polarization spectral phenomena. Okay, so this figure shows the ensemble average, Van Sitter-Zernike theorem. Okay, so once we have, let's say, the birefringent polarization scrambler. Okay, when the laser light passes through this scrambler, okay, we can observe a random electric field just behind it. Okay, here the electric field just it's completely random. If we are able, to measure the spatial, let's say, to measure the ensemble average, concept for the generalized Stokes parameter. Okay, we can get the generalized Stokes parameter at the observation plane. So here shows the, let's say, the equations, okay, for the ensemble average Van Sitter-Zernike theorem. As you see here, this S is the Stokes parameters at the scattering plane, and the definition of ensemble average Stokes parameter. And at the observation plane, that is that represents the ensemble average, generalized Stokes parameter at the observation plane. So through this, ensemble average Van Sitter-Zernike theorem, okay, we are able to make a link between the scattering plane and the observation plane. Now, okay, let's just come to some important concepts about the autocorrelation functions of the Stokes parameter. As you see, now this conference is mainly focused on the correlation optics. So here we just try to give a more just detailed definition for the autocorrelation of Stokes parameter. So in this sense, okay, the autocorrelation of Stokes parameter is defined as the ensemble average of the Stokes parameter at the different locations. Okay, so with the aid of the complex Gaussian moment theorem, okay, we can express the autocorrelation functions of Stokes parameter, like in this way, So here, as you see here, the capital L, okay, represent the 4 linear transformations, okay, defined in this way. So these 4 linear transformations will play a very important role to understand or to describe the correlations of Stokes parameter. So as you see here, through these 4 linear transformations or linear, so they are just changes the signs for the different term, but basically, okay, through the different just combinations, we are able to get the autocorrelation functions for the different Stokes parameter. And here, SL hat represent the normalized Stokes parameter. Normalized Stokes parameter. So this is the expression, okay, which has been obtained by using the complex Gaussian moment theorem, and also with the definition for the generalized Stokes parameter. So since, let's say, if we just assume that at the illumination illumination plane, okay, the scattering spot is a circular scattering spot. So by using the Van Sittard-Zelig theorem, okay, we are able to calculate the autocorrelation functions of the Stokes parameter at the detection plane. So here shows the final expression, okay, where the P represents the degree of ensemble average of polarization. And here S hat represents the normalized Stokes parameter. And here we have the, four linear just, combinations or linear just transforms for this, normalized Stokes parameter. And here that is the typical, area pattern at the, in this expression. Okay, and these figures shows the distributions or cross sections for the autocorrelation function at the observation plane. Okay, as you see, basically, since the scattering plane, we have the different the component for the Stokes parameter. So at the observation plane, okay, the height of these correlation functions are different. So that is a typical just distribution for the autocorrelation functions of Stokes parameter at the observation plane. And meanwhile, okay, as you see, okay, for each different curve, okay, there are different bias or some background. Okay, if we are able to, just remove all this bias background, and also, through the let's say the DC subtracted component, we can also introduce some concept is related to the Stokes correlation area. So as you see in all these dashed frame, okay, that is give the definition for the Stokes correlation area, okay, for this speckle, for this polarization speckle, okay, which shares some formal analogy to the conventional definition for the average size of the speckle for scalar speckle, So this is just have been this just area is a polarization dependent correlation area. Okay, so besides the autocorrelation functions, okay, of the Stokes parameter, we are also interested in the power spectral densities of Stokes parameter, okay, which is the Fourier transform of the autocorrelation function. Okay. Since we have already derived, the autocorrelation functions, so yeah, after Fourier transform, we can obtain the corresponding power spectral density. Okay, as shown here. For each, each Stokes parameter, we have the different DC component for its power spectrum. The power spectrum, okay, is mainly is mainly controlled by the the amount of by the amount of the Stokes parameter in the field in the field. And besides this DC component, we also have the AC component, AC component. So this is for this is just the AC component. For each just the AC component, okay, we have the height are different. The height are different. So therefore, okay, so the power spectral densities of the Stokes parameters are also different for the polarization spectrum. This is just a general result. Okay, then this slide shows a particular result. Okay, if the polarization spectrum is isotropic, so it means that if the degree of ensemble average polarization becomes 0, okay, we can see that the autocorrelations for the S1, S2, and S3 will coincide, become the one curve, and with its DC component becomes 0. And now the autocorrelation functions for the S0, okay, we have a different background, and similarly, okay, the height, let's say the AC component for the power spectral density of the Stokes parameter, okay, for the AC component also coincide to the one curve, and we only have the one DC component from the S0 for the power spectrum density of the S0. Okay, then the AC component for the other Stokes parameter disappear. So this is a special case for the autocorrelation function and the power spectral density of Stokes parameter. Okay, now let's move to the different topic about the statistics of the integrated Stokes parameter. So it's related to the polarization sensitive detection of stochastic electric fields. So as we know that, in order to detect the Stokes parameter, okay, so, we are familiar with the 6-step approach, okay, which is, just well written in any textbook related about the polarizations, okay. So here shows a typical example, okay. So in front of the camera, CCD camera, okay, if we change different polarizing filters, okay, and through the different combination of polarizing filters, we are able to calculate the Stokes parameter based on its definition. Yeah. So here shows one example of different. Here shows typical just intensity distributions of the detected speckle pattern. Okay, so based on definition, okay, we are able to obtain its Stokes parameters. So here, through the different combination P and the Q, okay, represent a different combination. Okay, for example, if the P represents the linear polarizer along the horizontal, and the Q represents the linear polarizer along the vertical directions, we can just use this way to get the S1 Stokes parameter. And if the P represents the 45-degree, the linear polarization, linear polarizer along the 45-degree, and the Q represents the linear polarizer along the 135-degree, we are able to get S2. Similarly, if the P represents the right-handed circular polarizer, and the Q represents the left-handed circular polarizer, we are able to get S3. Okay. Through this different combination, okay, the Stokes parameter can be obtained, okay, based on its definition. But okay, for the practice, as we know that the Stokes parameter is observable in physics. Okay, so for any Stokes parameter cannot be measured at an ideally point without geometrical size. Okay, so any detector has its just wide or just aperture for detection. Okay, so therefore the measured Stokes parameter are always integrated version of the ideal point Stokes parameters. So here shows a typical pattern. Okay, let's say within the red frame. Okay, that is the size of pixel or the size or just aperture of the detector. Okay, so within this just aperture of the detector. Okay, the instantaneous Stokes parameter changes. Okay, so we are always just obtained is integrated Stokes parameter. So here just show you definitions of integrated Stokes parameter. Okay, and you know, as you see through the here the D represent the distributions of the detectors. You know, the sensitivity for photosensitivity over space, and AD is the size or area of this just detector. Okay, through this kind of definition, okay, we are able to introduce the integrated Stokes parameter. When we give this definition, of course, here we have already made use of the assumption that the signal itself is spatially ergodic. Okay, and as that is the case in the in our experiment. You know, in the experiment itself, the polarizing spectrum itself is it's a stationary. Okay, we only change the polarizing filters. So it means that the detection area is still the same, but only change the different polarized filters. So we use the same D, okay, for this detection process. Okay, so now let us see some statistics of this integrated Stokes parameter, because the integrated Stokes parameter is the is a detectable Stokes parameter, not the ideal theoretical Stokes parameter. Okay. And so based on the definitions, okay, for the integrated Stokes parameter, we are able to get its means. Okay, through this definition, you can quickly see that each means of the detected integrated Stokes parameter is identical to the true mean value of the Stokes parameters incident on the detector. So it means the detected Stokes parameter, the average value for the detected Stokes parameter is really equal to the true instantaneous true mean value for the instantaneous Stokes parameter. Okay, we are also able to calculate the variance of integrated Stokes parameter. Okay, through the variance. Okay, we can see the detection and the accuracy. Okay. So in the definition of the variance for the integrated Stokes parameter, as you see here, we have the squared component for the integrated Stokes parameter. And based on the definition of integrated Stokes parameter, we see that in this expression, then the Stokes autocorrelation plays an important role to determine the variance of integrated Stokes parameter. Okay, that once again, that's at least one important application of correlation of Stokes parameter. Okay. And here, the terms in the red frame indicate the correlation of the detection, windows. Okay, so once again, this is another type of detection, another type of correlation. So anyway, the variance is strongly influenced by the correlation of different physical quantities in the experiment. Okay. So after substitute the obtained the autocorrelation functions of the Stokes parameter, okay, we are able to get the variance of the integrated Stokes parameter as shown here. Okay. Next, we will choose M here, M for the referred to as the numbers of degrees of freedom for Stokes parameter detection. After introducing the M, okay, we can simplify our just expression for the variance of integrated Stokes parameter in this way. So here P bar represents the degree of ensemble average polarization, and M represents the numbers of degree of freedoms. Okay, so it means that here the variance detection for the detected Stokes parameter is strongly influenced by the let's say degree of ensemble average of the ensemble average of polarization of the field itself, but also related to the numbers of the degrees of freedoms for the Stokes parameter. Here, these numbers of degrees of freedom is not only is being determined not only by the field itself, but also by the detection condition. Here, gamma D represents the detection condition. And based on this definition, we can also obtain the signal-to-noise ratio for the integrated Stokes parameter. Okay, so as you know that the Stokes parameter S1, S2, and S3 may take a positive or negative value. So it means that the mean value means for the Stokes parameter S1, S2, and S3 may take the 0 or negative value. So in order to be more sensible for the definition of a degree of for the signal to noise ratio. For the signal to noise ratio, okay, here this signal to noise ratio has been introduced in the power sense, not as the conventional IMS sense, the signal to noise ratio. So once we introduce this signal to noise ratio in the power sense, okay, after calculation, here we can just see here the signal to noise ratio can be represented in this way. So once again, M and P, okay, have a strong influence to this signal to noise ratio for the detection of the Stokes parameter. Okay. Now let us take a little bit more close look at the numbers of degrees of freedom for the detection of the Stokes parameter. Okay, based on the definition. Okay, this is the definition for this newly introduced degrees of freedoms of numbers of degrees of freedoms for detection of Stokes parameter. Okay, we can just have some more detailed just a calculation. Okay, so once the let's say the correlations, okay, of the once the generalized Stokes parameter has been given for the instant field itself, we are able to calculate these numbers of degrees of freedom for the detection of Stokes parameter. So here shows the two limiting cases. The first one is showing here. This is showing here in the right side figure. If the speckle size is much larger than the detection area. So here, each red frame represents the pixel size. So here, our speckle size is much larger than the pixel size. So then we have the degree, we have the numbers of degree of freedoms. Okay, for detection of Stokes parameter, can be simplified in this way. Okay. So another opposite case has been shown in the right side figure. Okay, as you see, within each pixel, the speckle, okay, there are a lot of speckles inside one pixel. Okay, so under this opposite case, okay, the numbers of degrees of freedom for detection of Stokes parameter can be simplified as a different form. Okay. And in order to see the performance for this newly introduced numbers of degrees of freedom for the detection of the Stokes parameter, okay, we have drawn this plot. Okay, as you see here, the MS naught, is the same as the conventional one, conventional numbers of degrees of freedom, okay, for intensity detection, okay, which has been well known for the for statistical optics. Okay, and besides the MS naught, we also have the MS1, MS2, and MS3. So, and the left side figure, as you see, if the speckle size is much larger than speckle size, okay, we have the flat curve at the right end. At the left end. If the pixel size is much larger than the speckle size, okay, as you see, this M is a linear proportional increased as compared with compared with the area size of speckle. So this is just more general case for the newly introduced number of degree of freedom. And this figure shows a special case for the isotropic polarization speckle. Okay, and for the isotropic polarization speckle, okay, we have the degree of ensemble average polarization P equal to 0. So all these four curves are for the numbers of degrees of freedom for detection of the Stokes parameter coincide into the one curve. This one curve is the conventional. Okay, that's the, let's say, definition for the numbers of degree of freedom. Okay, for detection of the intensity. So these figures we are familiar, but only at a special case these four curves coincide to one curve. Otherwise, we will have the four separated curves M. Okay, which just gives gives a different performance for the detection process. Okay, so besides the means and the variance of the integrated Stokes parameter, we are also interested in the in the distribution of the integrated Stokes parameter, because let's say the integrated Stokes parameter is the real measurable Stokes parameter instead of the the instantaneous Stokes parameter, which is the concept cannot be measured directly. Okay, yeah. So here just we use the boxcar approximation to get the to approximation for the instantaneous Stokes parameter. Try to find the distribution. Try to find the probability density functions of the integrated Stokes parameter. So as you see, for each the dashed line, give us it represents the continuous varying instantaneous Stokes parameter, and the boxcar functions represent the integrated Stokes parameter. So within each pure box, we have a constant value for this for the detected Stokes parameter. Okay, so this is the definition. Okay, definition. So through this kind of boxcar approximation, okay, we can just we can just make such kind of representation in this way. Okay. So after some kind of calculation, we have already obtained the approximated probability density functions for all these integrated Stokes parameter. So here shows the result. Here this is the expression. Here shows the result. Okay, as you see, as you see that for the different degree of ensemble average polarization, we have a different distributions for all these integrated Stokes parameter. And meanwhile, for M, okay, plays a very important role to provide the experimental condition for the Stokes detection. Okay, even for the same field, different M will give the different curves. So this is for integrated Stokes parameter S0. Okay, then similarly, this figure shows the probability density functions for the integrated Stokes parameter S1. Same S1. Okay, so for the different degree of ensemble average polarization, we have a different distribution, and even for the same field, okay, with a different experimental condition for the different M, as you see, the detected the Stokes parameter are different. So it means that really the M plays a very important role for the detection of the Stokes parameter. And this figure shows the probability density functions for the integrated Stokes parameter S2 and S3. Basically, S2 and S3, have the same distributions. If we just if we apply the unitary transformations to the optical field itself. Okay. So as you see, once again, we can observe the similar, properties as before. Okay. Now, through all these results, here I have listed some kind of observations. Okay, so first, okay, it is enough to say that, okay, when M(S0) is equal to 1, the distribution for the integrated Stokes parameter resemble the familiar distributions for the instantaneous Stokes parameter. So as you see, so from here, as you see, when M equal to 1, all these results, okay, are similar to our, similar to the instantaneous Stokes parameter, which are well known. Okay, are well known. Okay, so here is M1, M1, and M1. When M, okay, close to infinity, all these density functions will approach to a delta functions centered as its mean value. So as you see, so if let's say M become larger, so all these, just distributions, is close to impulse functions, direct functions. Okay, when M become infinity. Okay. So, but for a large but finite value of M, okay, the center limit theorem tells us that the density distributions for the integrated Stokes parameter approach Gaussian distribution. Gaussian distribution. See here, for the finite value of M. So all these just distributions similar to the Gaussian distribution. Okay. So through all these observations, okay, we see that in order to detect the instantaneous, just Stokes parameter for the stochastic optical field, okay, we would like to try to create design or to create our experimental condition for the M, is close to 1. M close to 1. Okay, as you see from the previous figure, M close to 1 means that as here, as the left side. So it means that, so the speckle size should be much larger than the pixel size. Okay, several years before, we have already presented some kind of our experimental results, okay, for detection of the first order statistics. Okay, so here shows the result, the histogram of the histogram of the detected Stokes parameter, and which is close to the instantaneous, Stokes parameter theoretically observed. Okay, so this shows the result of the S1 and the S2 and the S3. So all these results are experimentally detected results. So today we have already shown provide its underlying physics, okay, to say that so why the speckle size should be much larger than the pixel size itself. And now let's move to the final topic of today's
the chairman speaking. Why?
Okay. How many minutes do I have?
It will be time to conclude, I think, respectfully from the timing.
Okay, I see. Thank you. Yeah, okay. So now I will quickly just go through the final topic about the Stokes vector interferometer. Okay. So as we know that the Stokes, let's say the intensity correlation or cross covariance of intensity plays a very important role. Okay, for the intensity interferometer, photocorrelation, and just which gives us just basic principles for the different kind of intensity interferometer used before. Okay, this figure shows the photon ghost imaging pattern. Okay, so here the key point is the calculation of the cross covariance of intensity. But so far, so all these kind of results are related to intensity. So here we propose a new interferometer referred to as the Stokes vector interferometer. So that is the basic structure. Okay, due to the time, I would like to quickly go through. The idea is the following. Okay, once we detect the instantaneous Stokes parameters, okay, at the two different locations, okay, by calculation of the cross covariance for the Stokes parameter at the different location, we are able to have its cross covariance matrix for the Stokes parameter. And based on all these calculated cross covariance matrix, okay, we are able to reconstruct the generalized Stokes parameter, the modulus of the generalized Stokes parameter, and the relative phase of the for the generalized Stokes parameter. So here this figure shows the block diagram of the Stokes vector interferometer. And here shows the more detailed mathematics. Okay, so first let's say we subtract the DC component for the detected Stokes parameter and calculate compute its the cross covariance matrix. So for all these 16 elements of the cross covariance matrix for the Stokes parameter, okay, then we can just make use of these 16 elements, okay, to detect the signal. As you see from the diagonal components, 4 diagonal elements of the cross covariance matrix, okay, here that's the diagonal components of this matrix. Okay, we are able to reconstruct the squared moduli for the generalized Stokes parameter at these 2 positions. And by the normalization, okay, we are able to get the squared moduli for the normalized the degree normalized Stokes parameter. Okay. This is that. And besides the diagonal component, we also just interested in the off diagonal component of the cross covariance matrix. So here shows the express. Okay, so now from the off diagonal elements in the matrix for the cross covariance of the Stokes parameter, the relative phase, okay, for the generalized Stokes parameter can be retrieved in this way. So here, let's say just for for each generalized Stokes parameter is a complex function. Okay, so we can have the through with the phase difference for the generalized Stokes parameter. Okay, for the delta phi naught is 0 and delta phi 1 is the phase difference of the generalized Stokes parameter S1 as compared with S0. Okay, we can retrieve all these results through the off diagonal component of the matrix for the cross covariance of the Stokes parameter. So here shows the expression. Okay. Now I will quickly show you this.
I'm sorry, we need to stop.
Okay.
Because we have time. No time we have.
Okay. Okay. I stop.
Please finish. Finished. Thank you.
Okay, so this is the experimental result. Okay, finally we are able to retrieve the squared moduli and the relative phase for this result. So that's the conclusion. Okay, thank you very much. That's all.
Thank you, Wang. So we are running short regarding timing. So I would suggest to move to the next talk if Stine is ready. And may I
Please, if you have some questions, please in chat, because we haven't time according to the timetable. And if you have some questions in chat.
The chat is still open for question, of course. So could you unshare your presentation so that Stine Hanson can share his own once to start his presentation, please?
So, can you hear me?
Yes, we hear you. So I'm pleased to introduce Stine Hanson from Denmark Technical University, and he will present a work, Coherence-based investigation of stellar objects, theoretical approach, 20-minute contributed talk, including question. Thank you, Stine.
Thank you.
Please go
I'll
ahead.
try to share my screen.
Yeah. Not yet.
Let me see. This is the one. Share. Let me see.
Yes, looks like it's, yes, we got it.
Yes, and so I should have the start. Could I start?
Yes, sure, you can, please.
I can do that from beginning. Can you see me and can you see the screen?
Yes, all is fine. You can go.
Thank you. Thank you. As I said, these authors are the same as for the previous presentation. So I'm an old scientist, so therefore I dare to propose something which might be wrong, but I hope I will have no questions afterwards. So the overview of my presentation is the prerequisites. I'll show the space-time covariance and theory for Gaussian fields. And I'll give two examples where it can be used, and that's the difference in Doppler shift for closely spaced objects, and it's the angular twist from in-plane rotation of distant objects. And future investigations, that's primarily for students who could be interested in pursuing some of these ideas. I talk about stellar objects, but it could just as well be for measurement systems in the laboratory. And if everything goes correctly, I'll come with conclusions. So my prerequisites are, I have influence of optical turbulence, it's not included, neither are relativistic effects. I use a scalar approach, and I'll do not a profound investigation of previous work will not be provided. And I simplify everything by using canonical transforms, that's more or less doing Gaussian functions all the way, but I do that in order to pave the way to make it easier to see what the results I come up with. And I think the theoretical investigations is valid for any wavelengths in the electromagnetic spectrum, and probably more relevant for radio waves. So they start out with two stars, with a distance delta x at a distance L, which might be light years from here. And we are down at the ground where we have two detectors. Sometimes we only have one, two detectors, point detectors, and the distance is very large. And we are primarily investigating the observed fields from incoherent emissions from the objects. So we don't have any coherence for the time being. So now we make one measurement, and we have, for the second measurement, a movement of the particles or the stars actually displaced. And I have a small view here of two particles. So I want to see what happens, what can be deduced from the two detectors if the two particles, the two stellar objects, are moving at a distance delta C1 and delta C2. So it's delayed, it's the delayed space-time cross covariance I'm looking for. So the field at the ground, U of P, comma, delta tau, that's the time delay, is equal to the field at the object times the Green's function. And being very far away from the object, the Green's function becomes very simple. It's just a sum of wavelets coming from the object R to the observer P. It becomes very simple. So the field at the object, one object placed at plus delta x divided by 2, and one at minus delta x divided by 2. And so delta x is the distance between the two objects. Omega 0, that's the size of the object. So when I'm using this, omega 0 will be much smaller than delta x, but we are not able to resolve the two objects, neither the distance between the two objects at the ground. We, of course, have the power and we normalize with omega 0, but we have a phase function, which is dependent on r, comma, tau, and we have the phase functions due to the velocity of the two particles, v1 and v2, and we have the time delay tau. Furthermore, as I said, we are working within the canonical transform. That means everything is Gaussian, and so will the spectrum for wave number b. That's a Gaussian distribution centered at k0 with a width delta k. But we are talking about incoherent light. That means that's the emission from the stars themselves. Therefore, we have a delta correlation. This is the field at one position times the field at an adjacent position, R2 and R1, at the object at two different times, tau 1 and tau 2, and two different k numbers, wave numbers. Angular brackets here indicates for me ensemble average. So we have a delta correlation in the wave number. We have a delta correlation in the space at the two positions. So we are almost ready. What we see is the cross correlation. That means the ensemble average of the intensity at one position P1 at time tau equal to 0 times the intensity at one detector at position P2 at a later time delta tau. That can be written as the sum of the fields from the two stars, sum of the two fields from the two stars at a later time delta tau, and ensemble average of everything. That will give 16 terms, which is too much for me to do because I'm an old scientist. So I have to make something which is a little easier. But the information carrying part is given by the cross covariance. That's the cross covariance, that's the cross correlation minus the DC part, more or less the DC part, which has no information for us for the time being. So we end up by having the cross covariance at two different positions at the ground with this difference in time delta tau. So this is the cross correlation minus the DC part, and we write that up ensemble average of the field from one stellar object at position P1 times tau equal to 0 at sum of the field from the second particle, second stellar object at the same position, times the same for the field at an adjacent time delta tau. So this will end up with the angular brackets to be an ensemble average over 16 terms. So this is what I wrote previously, but we essentially have two different kind of terms because we have used the Gaussian theorem that makes fourth order correlation functions into products of second order correlation functions. So now we only have ensemble average of 2 fields, 2 fields, 2 fields, and 2 fields. But everything has to be absolutely squared. We essentially have 2 different terms, namely the self terms, that's the field at position 1 times the field at position 1. I'm sorry, at position 1 times the field at position 2 at delta tau. And we have, that's the one coming up here. And we have the mixed terms, that's the field from one star times the field at an adjacent star. That's these terms. But if we take the mixed term first, that's the one from 2 different stars. We write it up. We have the Green's function connecting the field in the input plane with the field in the output plane at K1 times the field in the output plane with the field in the input plane at another wave number K2. We come up with the ensemble average of the field in the input plane for star number 2 times the one from star number 1. And we have to add or introduce the K numbers as well. But if we look at this, we see that there's no overlap between the field from 2 different stars. Therefore, this will become 0. And that make me very anxious, because does this mean that the Young's interferometer effect disappear? So there's no interference from one star to the other. And if you refer that to the Young's interferometer, you have the 2 holes, and there is definitely interference between the 2 holes. So that didn't make my day for 3 days, where I ponder what was going on here. So my problem was that I assumed delta correlated fields in the optic plane, and that's responsible for the disappearance of this term. If I had a finite degree of spatial correlation in the input plane, this would violate the Gaussian assumption and make Young very happy again. But in our case, this cross term between the fields from 2 different stars disappear. So we only have this self term, that's the field from star number 1 at tau t equal to 0 times the field from star number 2 at a later time delta tau. That's the only thing we have to calculate. And we get the cross covariance, time lag cross covariance, time lag delta tau, and space correlation between 2 different points, P1 and P2. And that ends up as the 2 times the real part of the field from star number 1, ensemble averaged, the brackets here, times the field correlation from star number 2 with delta tau. And we have discarded 2 DC terms. Now it becomes easy for us to calculate, because we know the Green's function, we know the wave number distribution, and we know how to calculate it for the intensities. And if we do the calculations for just having one detector on the ground, that means P1 and P2 is equal to 0. We do all the math, and we end up with an expression which contains the cosine VZ1 minus VZ2, and that's exactly the difference in Doppler shift between the 2 stars. So by doing this, we should be able to derive the difference in Doppler shift between the 2 adjacent stars, even though we cannot resolve them. But furthermore, we also have a kind of decorrelation term here. If delta C and delta C2 becomes too large compared to delta K0, that's the spectral width of the light or the radio transmission, radio emission, this will quench the cosine term. But we have the frequency, the Doppler frequency you measure is K0, that's the wave number, the average wave number, times the difference between the two velocities, and we have the 2 pi, of course. So what we will see is an amplitude burst with the right Doppler difference frequency, and with the number n of contiguous oscillations, where n is equal to K0 divided by delta K0. We, of course, need a very narrow bandwidth for the light we detect or the radio emission, and it's independent of actual velocity difference. The correlation will set in when delta Z1 plus delta Z2 is larger than 1 divided by delta K0. We need a very small width in wave number. Now, if we have 2 lateral displaced point detectors, not only 1 point detectors on the ground, but 2 laterally displaced detectors with displacement delta px, we again get a lot of crap in front, but we get the velocity. Here is the Doppler velocity, but we have a phase term. So by displacing or measuring the covariance for 2 different positions, we can get the phase term. That means we can get the quadrature signal, we can get 180 degrees, and we can even get spectral narrowing by picking out the right delta px as a function of delta x, which was the difference between the stars, and L is the distance. So the distance between the 2 detectors should be lambda divided by 2 alpha, where alpha is the angular distance between the 2 objects. What will happen if the object not only moves in the axial direction, but also transverse direction? And that can be shown it's not really important. It should move quite a lot before we have decorrelation of our speckles. Now, if we not only have 1 or 2 stars, but we have a gathering of stars which cannot be resolved, we can get the time-lagged cross covariance with the sum of all the particle pairs, and we get all the difference Doppler velocities from each pair of single particles in the cloud. And if we can further get the phases, we might do an inverse Fourier transform, and we can end up with a part of the Van Hove space-time correlation function for the objects. Next, and the last part I'll use is the unresolved single rotation galaxy of width omega 0 with axis pointing towards the observer. We will change the Green's function into cylindrical coordinates. That means x, r, cosine phi, that's in the object, r sine phi, still the object, and on the ground we have capital P and theta is the cylindrical coordinates. The Green's function are now given by P and R or P, that's the radial distances, and the phases. We immediately see that we only need the phase difference between the object and the observation point. I use the K0 wave number in front and use the variable K here because it could be important, but it turns out that K is not important, that it moves a solid object. The Green's function, we have all the time lag cross covariance we have to perform is the integration of the 2 R's, the 2 phi's, that's the input plane, the stellar plane, and integration over wave number, and we have the Green's function, and furthermore we have the ensemble average of the field in the stellar object plane. We assume that the object moves as a frozen object. That means we invoke Taylor's hypothesis. That means the field at 2 different positions in the input plane is delta function of R1 minus R2 but it's not a delta function between the two angular position phi1 and phi2 because we have a movement delta phi of the object. We can now do the integration for a single detector, and we get a very neat example here. P, that's the position at the observation. Rho, that's the speckle size, which is L divided by K omega 0. Omega 0 was the size of the rotating object. L is the distance and K is the wave number. We have delta theta minus delta phi. That's the difference in angular position from the object to the observation point. So we have P here. We move away from the center of the rotational axis. Here, we are just underneath the axis of rotation, and that'll be very seldom we can reach this point. But as we move away, we see that we have a high correlation when delta theta minus delta phi is equal to 0. Of course, we also have the same for pi and minus pi. But as we move away from the center, P going away from the center of the axis as it hits the ground, we can depict what is the rotation of the object under investigation. But two detectors have to be placed at the same radial distance, and that becomes very complicated indeed. Maybe not impossible, but we need a couple of detectors on the ground or up in the air in order to see the rotation of the object.
Chairman speaking, Sin,
yes.
it will be time for conclusion.
Yes, the conclusion is we have two projects for students. See what happens if you have a rotation forward and two detectors on the ground. Project number 2 is see if you have Fraunhofer lines from the object, and we have two objects with two different Fraunhofer lines, and we have a shift due to Doppler shift, and the mathematics for darkness or interference of darkness is similar to the one for light. Conclusions: quasi-optical coherent fields are established during long-range propagation combined with spectral filtering. Diffusion time for the objects have not been included, neither has optical turbulence. And some neat students' experiment would come in handy. And I would say we might not be able to detect dark matter, but we can detect what matter. Thank you for your patience.
I will take only one question because of the short timing. So, Igor, please.
I am not expert in the star mechanics, but when you said about the Doppler effects, you written the cosine where we have the difference between velocities of stars. Where's the direction of its movement?
As I said, it's only the C direction, the C displacement I've analyzed, but I had a slide saying what happens if at the same time the ensemble of the two stars will move transversely, and that gives very little decorrelation. It could give, it doesn't even give a phase change, but if one star moves laterally with respect to the other during experiment, it'll give a phase change, but the decorrelation is not very large due to the large distance to the object.
Thank you.
Thank you. So let's move on to the next talk. So we need, thank you.
Okay, so I believe our talk is next in the program. Is that correct? If so, let me start sharing my screen.
Yes.
Okay, excellent. So
So Rostislav is present adapting illustrations for people with low vision.
Yep, that's correct. So
detection methods. Thank you.
Yeah. Okay. So this talk is going to be a more sort of applied computer science discussion, and it's going to focus on using edge detection, a computer vision method, as a way of helping people with low vision to better interpret and understand printed literature, which often can be somewhat inaccessible. So we're going to have the following sections in this talk. First, I'm going to explain edge detection as a concept, its history and potential application. I then give a detailed overview of a simple edge detection method, canny edge detection, go over the current state of the art, so deep learning for edge detection, and give a summary and provide some conclusions on our further research in this field. So, edge detection is a task of finding edges on an image. Those are boundaries at which some significant aspect of the image changes. So typically those are, for example, boundaries between objects or an object in the background or similar areas within the image. By analyzing aspects of the image, such as pixel intensities, edge detection methods can discover areas where different parts of the image rapidly change. Those can be used to separate an image into multiple regions or identify specific objects or perform more applied tasks such as fingerprint recognition or robotic vision. So some of the first edge detection algorithms date back to the early days of computer vision research in the 1960s and 1970s, with research such as looking for ways to mimic the human ability to easily distinguish between different objects in images. And one of the earliest edge detection methods was the Sobel operator, which used simple image filters to approximate the gradient of pixel intensities, which is a common technique to discover different regions within an image, basically looking at pixels within certain limited locations and computing their gradients to discover whether there's an edge at a certain location. The widely used even today canny edge detector was proposed by John Canny in 1986 and introduced a more complex multi-stage algorithm with both pre-processing and post-processing steps, in addition to calculating the gradient magnitudes I've previously mentioned. And with the advent of deep learning, particularly convolutional neural networks, there was another significant advancement to edge detection, as researchers began training neural networks to identify edge maps on input images, bypassing the need for handcrafted filters and thresholds. Edge detection has been applied in a variety of fields to locate objects within an image, which includes generalized object detection and tracking, for example, in a self-driving vehicle, image understanding and visual question answering, basically determining whether there is a certain kind of object on an image, for example, medical imaging, such as detecting tumors within certain scans, computer vision, robotics, and so on. However, a novel application for this image processing technique is actually enhancing the accessibility of illustrations for people with low vision. So many illustrations in both electronic and printed publications alike present challenges like insufficient contrast, small details, or densely packed visual elements. And the outputs of edge detection algorithms can significantly emphasize the boundaries between objects in an image, making them more distinct and perceivable, which enables readers with low vision to view and comprehend the illustration. So one commonly used edge detection algorithm is canny edge detection. By classical, I refer to a method not involving the use of convolutional neural networks or deep learning, with the output being simpler as a result, but easier to implement and more performant. It involves multiple steps in its process, and here I'll go over them one by one. So the initial step of this algorithm involves applying a Gaussian filter to the input image. This transforms or essentially blurs the image in order to reduce the noise within it and create a more reliable result in the further steps of edge detection. So this, as you can see, is determined by the following formula, this kernel, and it works on a per pixel basis. So here, sigma represents the standard deviation of the pixel distribution, which is calculated based on the overall image, and x and y are selected based on the filter size. And the way it works is basically by multiplying a matrix over parts of the image until it's essentially reduced to this small blurred version. So the next step is gradient calculation. And in this step, the derivatives of the Gaussian filter are calculated with respect to both 2D dimensions, so x and y. Essentially, this uses a simple detection kernel. For example, it's Sobel in the algorithm's implementation in the library OpenCV, and calculates a gradient vector with the following magnitude and direction. And next, a process called non-max operation, which is here shown on a similar algorithm, it basically makes the edges detected by the kernel thinner by removing pixels with unwanted gradients. In order to do this, the algorithm determines the magnitude obtained in the previous step, and decides whether a pixel forms a local maximum in the direction of the gradient. If the pixel does not form a local maximum, it is suppressed. And the next step is double thresholding. This final stage of the algorithm determines which edges are considered real and which are discarded as those being caused by leftover noise. So once again, we filter by the gradient value or magnitude and determine a maximum and a minimum. Edges with a gradient higher than the maximum than minimum are considered real edges. Those lower than the minimum are discarded, and edges in between are discarded unless they are connected to another confirmed edge. So the output of the kernel detection algorithm is typically an image where the edges are white and the rest of the image is black. But for our domain, we invert this to produce something resembling a paper sketch or an illustration. So in figure 1, we can see that it correctly detects the object located within the image, so an elephant. But there's still plenty of noise in the default settings of the algorithm. So luckily, the user can adjust the parameters of double thresholding to produce an image with more visible edges, but more noise, or a more filtered version of the line art. So as you can see, while pretty decent, it's still not an ideal output. And that's why in practice, we're going to be using deep learning for edge detection. So current state-of-the-art deep learning methods leverage convolutional neural networks to detect edges in images. And while classic edge detection algorithms work with inferred data like pixel gradients, CNNs learn features directly from raw image data, typically trained to work with images of a certain size, like 512 by 512 pixels, and basically learn mappings from those images to edges directly. As with other deep learning algorithms, this typically requires training on large datasets with labeled edge maps, where each image is manually annotated with its basically correct representation as a set of edges. Those datasets are typically much smaller than those used in many problem areas. So examples such as BioPad feature as few as 250 images, and there are ways to enhance them a little bit further. So an edge detection method utilizing deep learning is typically built on top of a pre-trained computer vision CNN, such as VGNet or ResNet, and is adapted to produce edge maps from input images. So one deep learning algorithm, which you can see has a much more impressive output, is holistically learned edge detection or HED. This method outputs a mapping of an original image to an array of scores between 0 and 1, indicating how likely it is set at the specific pixel and edge is present. You can see for likelihoods of 1, this pixel is colored black, and for small likelihoods, it is colored gray, producing a sort of a sketchy representation of the image. For visualization purposes, the output is typically normalized to values between 0 and 255, which is what is done on this output image. In order to generate this mapping, HED uses a side output architecture, which means that there are several convolutional layers, and each is attached to a specific layer of the original CNN. So these side outputs essentially produce edge mappings with different levels of detail or resolution, and the final result is obtained by combining all of them. This algorithm was trained on the BSDS 500 dataset, containing originally 500 images, but with a process of data augmentation, like rotating and flipping the images, it was turned into a training set 32 times the size of the original. And you can see that this model's output can more accurately extract the main object located within the image, which is this elephant, as the animal structure is well outlined, and the only missing parts are in here obscured by some tall grass. Even less visible details such as trees in the background are quite cleanly separated. Now, a more modern architecture developed in 2020, dense extreme inception network for edge detection, differs from other state-of-the-art methods in that it doesn't use pre-trained models. It actually is an edge detection model trained purely on edge maps. Like HED, the model produces several side outputs and they can be combined in different ways. So a fuse method and an average method. One of those is another convolutional layer and the other is a simple mean of all of the side outputs. DuxNet was trained on a biped, a dataset specialized for edge detection, and it's shown to be the current state of the art method according to several metrics such as optimal dataset scale, which refers to F-score across the entire training dataset. So in this figure, we can see the method's output. As we can see, the fused and average outputs contain a similar number of edges. The fused output detects the animal as well as trees and even bushes. And the average output commences with further detected almost textures, such as those found on the elephant skin or on the road. And depending on whether a clean image or a more textured monochrome image is needed, either of those outputs can be utilized by the model's end user. So as a quick conclusion, we've shown that edge detection methods, especially those based on deep learning, can convert complex colored images to accurate monochrome representations, either producing a clean line-esque output or something containing the original image's texture. In the area of the assistive technologies, these models' capabilities can be used to produce clean, adaptive versions of illustrations, much more easily accessible by people with low vision. And further work in this field of research and our next steps involve producing a user-friendly interface, which actually allows a user like a books editor to convert an illustration into a wide range of adapted versions using multiple edge detection methods and selecting the best version for the needs. And this concludes our talk. I believe we might have some time for questions, even multiple.
Thank you. Indeed, we have time for questions. So there are several of them. So there is one from Irina.
Thank you for your presentation. I have one short question. My next question I ask you in chat, but now I want to ask you what can you say about this solution? Can the proposed solution be used for only electronic editions or for printing editions too?
Yeah, so actually a large part of our work is working with printed publications. In order to do this, we obtain from the publisher a version of the printed publication which was basically adapted for printing. It's usually a PDF file or something you convert to a PDF. And from that point, we can extract the images from it and work with them in the same way as basically an electronic publication. So yeah, it can be easily adapted for both of those. And as for the question in the chat, how exactly was it possible to increase the amount of trained data by 32 times?
Yeah.
So let's go back to the slide. So for this, we use a process called data augmentation, which is basically several image transformations that allow us to process it as essentially new images. So for example, for this image of an elephant, data augmentation can involve flipping it 180 degrees, rotating it by various angles, even focusing on certain areas of the image, so we can zoom in onto the head, for example. And it's been shown that even though this wasn't obviously adding like extra training samples, it actually increases the robustness of the training method a lot, because it works with like not only this image, but several permutations, and they are fairly easily to accomplish. They are just simple computational transformations. And yeah, it can significantly increase the amount of training data when you have a limited amount of original sort of samples. Is pretty much an almost mandatory step in most computer vision methods.
Thank you. All clear.
We had another question from Steen.
Okay.
My question is, what is criterion of the quality of edge detection? So we can see many results, but how to compare them?
Yeah, so the criteria for this is basically related to matching the edges produced by our methods with the edges found in the original datasets. As mentioned in one of the slides, one of those criteria is related to F-score. So basically we take an edge map, which is just a series of pixels. So in a normal dataset, we don't have these great parts, let's say. We only have something resembling the outline of the elephant, so it's basically an ideal edge map. And at this point, we use a formula to compare what our method produces and compare them to the pixels in the edge map. So ideally, we shouldn't have like these uncertain parts. They should be all fairly clean. Basically, the best method is selected by how closely it can match its edge map to what's located in the original dataset. So, for example, one common benchmark is something called, like I mentioned, ODS, or optimal dataset scale, referring to a way of computing F-score across the entire dataset while sort of scaling it so it appropriately represents the score.
Thank you.
We're still on time with the slot. So, Stevenson, if your question is still alive, you can ask it, and then we'll move to the next speaker. So, Steen, if you're here, if not, I will conclude the question session. Thank you, Rostislav. And I propose to move to the next speaker, who is already here. So, yeah.
It's me.
Yes. Hi. So, Rovisky.
Yeah.
I don't have the information from your affiliation on the program. Here, National Technical University of Ukraine in Kiev. So, please, you can start for 20-minute slots, including question. Thank you.
Ladies and gentlemen, my presentation is economical optical matrix to vector multiplier.
Oh, excuse me, Volodymyr. Could you perhaps make the full screen sharing?
Let me.
The attendees, if you can.
Okay, you can hear me?
We see, yeah, we see your presentation, but only on half of the screen. We see your folders list from your computer.
What?
Yes, we see your screen, on the screen.
On the screen?
Yeah. Переключіть так, щоб можна було бачити лише презентацію, а не всю це. То ви показуєте додаткову інформацію.
Yes, I see. Let me, I check the share. No, this is it. Share. It's good? Now,
yeah,
like this.
Perfect.
Yes.
Okay, thank you. My presentation is economical optical matrix to vector multiplier. I'm from National Technical University of Ukraine, Igor Sikorsky, Kiev Polytechnical Institute. So now we live in time of boost of interest to deep learning, neural networks, and other topics connected with them. And the key operation is matrix to vector multiplication, because we calculate neural network output like the multiplication of the vector of input signal to the matrix of the coefficient. At the same time, we live in the time of the boost of photonic integrated circuit, integrated optics, and integrated optics. So we live in the age of photonic artificial intelligence, and optical education should prepare a specialist, researcher, and engineer to this field. So the student should work with photonic artificial intelligence, not with the posters or lecture notes, but with the real devices. And when I studied the available optical matrix to vector multiplier, I found that it's no such device available for the universities. For example, this example is a lensless optical multiplier which applied Mach-Zehnder interferometer. Is experimental chip. This is another experimental chip. It used for optical multiplying a ring resonator, but it's not commercially available. The only exceptions was made almost 20 years ago. It's a famous and light optical chip which can multiply very big vector, 256 elements, to a very big matrix. It uses the two-dimensional cell of liquid, two-dimensional array of liquid crystal cells, but now it's not available. So the problem that we do not have the optical multiplier chip just to show them to our students, to organize the laboratory works with some optical multiplier, not the computer simulation. And this problem moved us, my PhD student Irina and me, to make some economical solution. So after information search and checking various variants, we selected a very simple and a very economical design. So our fully optical multiplier contains the set of one-dimensional array of optical waveguides. These waveguides, due to multiple scattering, make the integration of all incoming signal. Then we put the two-dimensional array of aperture. So it's ordinary metal films with the holes. And the next layer is the one-dimensional array of output waveguides. So idea is we put radiation into the upper layer signal, then waveguide made an integration, some radiation pass through the aperture, an area of these apertures are proportional to matrix coefficient. Then we integrate the results in the waveguides. If we get the economical and fully optical multiplier or matrix to vector multiplier. Possible application is neural network calculation of neuron output signal. It can perform the various integral transform from Fourier to Haar, and of course it can perform linear filtration, so we can do convolution and correlation operation. So the first version was easy because we plan the student will do them themselves. So design contains the unit. It's on the left is the first one-dimensional array of waveguides. On the center, the unit for introducing metal film with apertures, and on the right we have another one-dimensional array of waveguides that produce some output or some which collect output optical signals. So wavelength is all data presented on the slide, and this design allows to simulation of 4 neurons with 4 optical inputs. So the first version is the multiplier, which able to multiply vector of 4 elements to form a 4 matrix. But we use a differential mode. So to one waveguide, we put the signal if it is positive, and to the neighbor, we put the optical signal if the signal is negative. So formally, we produce the system with 4 waveguides, with 8 waveguides and 68 apertures. This is a photo of this unit. So we have assembled, disassembled photo. We have some, this first version of the aperture, of the two-dimensional of aperture array. And we made this array just changeable to introduce various matrix coefficients. And this we see the dimension of range of several centimeters, and we have of illumination units and detection units. So over there we can see the light emitted diode, and on the other unit we install the photo detector unit. To calculate the aperture or this array, the special software, very simple software package was designed, and it produced some elementary topology of the proposed optical multiplier. So we can set the number of input waveguides, the number of output waveguides. We can set the matrix of coefficients, and software produce the topology in OASIS format, that is readable various CAD software. Of course, this design is for students, and it has some advantages and disadvantages. Advantages is it's very fast multiplication because it's optical. It's formally it can work with multiple wavelengths. It's not sensitive to any high frequency electrical signal or field. It has simple design. So apertures are proportional to matrix coefficient, and it's economical. For us, it's very important. No expensive equipment is necessary for mass production. We use only 3D printing and laser gravity. But of course, this simple design has disadvantages. And the principal disadvantages is that we use the analog multiplication. And when we do analog multiplication, any amplitude distortion increase the error of the errors of multiplication. So the sources of the error is variation of characteristics, light emitted diode, photodetectors, various optical characteristics of waveguides, and the principal one is multiple crosstalk between the input and output waveguides. So unfortunately, we have the situation when some radiation come from input waveguides to output, and then the radiation come from output to the input, and then we have multiple crosstalk. But of course, we apply fixed two-dimensional aperture array, so we cannot change the coefficient during the working during the period when the optical multiplier works and dimensions of centimeter range. But summarized said above, we have a big benefit for optical education, and these benefits include all skill necessary to build this multiplier. So students should make optical measurements, connected and switching light emitted diode, connecting readout and amplification of photodiode signals, because the signals amplitude is rather small. So we need some rail-to-rail amplifier. A three-dimensional mechanical design, because they can make this their own design. No, not like this, for example. Include the laser graving, so they should to make some aperture ray and then produce it on film like this by accurate laser graving. Then, of course, electrical designs have attached electrical components. In the proposed design, we have the printed board is over there and there. So a light-emitted diode and photodetector fixed on the both sides of the illumination detector units. And elementary topologically design of photonic integrated socket, because it's not abstract, because they do this design for their device. Improving mathematical knowledge, matrix operation, integral transform, filtration, and others. Program development, because they need the right software to generate matrix of coefficients according to their network, neural network. And for me, it's very important understanding how neural network works, because they have the real primitive, real hardware. And of course, obviously, to see the perspective of photonic artificial intelligence. These multiplayer can be implemented in sensor robotic drones. And for us, very important is evaluation boards, because we need the evaluation boards with attached, which is attached to this multiplayer. It's make working explanation, it's easy and with good illustration. Now, we student has to attach measurement instruments to and power supply and some to these wares. We plan to produce, the next step is producing the evaluation board for this multiplayer and making some attempt to put it in to put this evaluation board with optical multiplier into robots. Thank you for attention. Please, I'm ready to answer the questions.
Thank you. So, question session is open. Irina? We don't hear you. We do not.
Is sound. Yeah. Thank you for your presentation. I have one little question. Can you say what processing data and calculation speed can be achieved by this device compared to traditional electronic multipliers?
This is instruments for students. So it cannot make some concurrent to NVIDIA board. So for us it's not instruments for very high volume, high speed calculation. It's this implementation of small neural network for robots and sensors, maybe for drone. So we can, this design is limited the number of neurons approximately up to 20. If we consider a very big multiplier, the error increased because the waveguide became dimensions, waveguide became bigger, and all sources of error increase and error increased. So this is not for massive calculation, it's for illustration of optical neural network and application of small neural networks in various units like sensors, robots, and maybe drones.
Okay, I see now. Thank you for your explanation.
I also take the question of Julia.
What is the price of this device?
Oh, very good question. Yes, for this first, we do not calculate precise because we made a lot of attempt to select. But if you go to restaurant, so the price of your dinner equal the price of the several devices like this one.
Thank you.
Thank you. So if no other question, I will give maybe the final words to Claudia, if some announcement should be made for the ongoing conference.
Thank you very much. Now we'll stop this part of session. We have a lunch, and at 2 p.m. we start the second part of our today's session. And I would like to note that you can change links because there will be with another link. And in afternoon we have only one session without parallel. Thank you. Have a nice lunch.
Thank you. Bye, everyone.